There are strange objects in the universe that exist in a state unlike anything we've ever encountered. These objects don't fully belong in the categories we've built around stars, black holes, or planets. They sit in a delicate balance, neither fully stable nor collapsing into oblivion, defying our understanding of physics. These are quasi-stable exotic compact objects, or kekos, and they could hold the answers to some of the deepest mysteries about the nature of space and time. Hidden from our direct observation, these enigmatic entities challenge everything we know about the cosmos. As we dive deeper into their secrets, we may uncover truths that could change our understanding of the universe forever. Stay with us, because the discovery of kekos could redefine the way we think about reality itself. But before we continue, subscribe to the channel so you don't miss out on any of these videos. The name itself, Quasi-stable exotic compact objects, feels like a riddle. Quasi-stable suggests something that is not quite permanent, but not transient either. Exotic hints at a nature beyond ordinary matter. And compact points to densities so intense that a sugar cube-sized amount could outweigh mountains. But unlike the fearsome black holes that swallow all light, these objects may hold the secrets to information preservation, quantum gravity, and the deepest mysteries of the cosmos. To understand quasi-stable exotic compact objects, we have to step back. Imagine a massive star reaching the final moments of its life. After burning through its nuclear fuel, gravity takes over, crushing the core into an incredibly dense state. Traditionally, depending on the mass, this collapse would create a neutron star or a black hole. But physics at such extremes is still uncharted territory. The theories we rely on, general relativity for gravity, quantum mechanics for the very small, clash violently at these scales. It's in this chaotic interplay that the idea of exotic compact objects was born. Instead of forming a traditional black hole with an event horizon, a point of no return, some theories propose that collapsing matter could stabilize into something else. Something that skirts the creation of a true event horizon, or only mimics it temporarily. These objects would be nearly as compact as black holes but with critical differences. They might reflect light faintly, or leak radiation slowly over unimaginable timescales. Some may even harbor internal structures fundamentally unlike anything known to conventional physics. What makes them quasi-stable is the delicate balance they maintain. They're stable enough to survive for billions of years, maybe even indefinitely under the right conditions, but still susceptible to rare quantum instabilities. These instabilities could, theoretically, cause them to decay over astronomical timescales, perhaps longer than the current age of the universe. There are many fascinating candidates proposed by physicists to fill the role of exotic compact objects. Each one paints a different portrait of how matter might behave under conditions where our current laws of nature begin to crack. Some theorists propose gravastars, gravitational vacuum stars, where a shell of ultra-dense matter encases a bubble of dark energy. In this model, the inward pull of gravity is balanced perfectly by the repulsive push of dark energy inside. Gravastars could be almost indistinguishable from black holes to a distant observer but would lack a true event horizon. Others talk about boson stars, hypothetical objects made entirely of bosons, particles that can occupy the same quantum state without limit. Unlike neutron stars made of neutrons, a boson star could be composed of exotic particles like hypothetical axions. They could be so diffuse as to be transparent, or so dense as to mimic black holes perfectly. Then there are even stranger proposals, fuzzballs from string theory, suggesting that black holes are actually enormous conglomerates of tangled strings rather than singularities surrounded by event horizons. The fuzz would prevent a true horizon from forming, solving some of the most stubborn paradoxes in physics, like the information loss problem. Imagine, then, that sprinkled across the universe are these quasi-stable imposters, quietly mimicking black holes without ever truly becoming them. They could be hiding in plain sight, pulling in stars, devouring matter, emitting gravitational waves, and yet, because they would lack an event horizon, they might behave subtly differently. Tiny differences in the ring-down phase of gravitational wave signals, for example, could betray their presence. Detection is one of the great challenges. Black holes are defined by their invisibility, after all. If an exotic compact object is nearly as opaque and dark, how could we ever tell? Researchers are combing through data from LIGO, Virgo, and other gravitational wave observatories, looking for tiny echoes or anomalies in the space-time ripples generated by collisions. A black hole merger should ring and dampen in a predictable way. A merger involving exotic objects might produce faint aftershocks, secondary echoes, as internal structure responds differently than a simple black hole. The stakes are monumental. If even a single quasi-stable exotic compact object were proven to exist, it would mean the death of the black hole singularity as a concept. It would force a reevaluation of general relativity in the strong field regime, possibly opening a window into the elusive theory of quantum gravity that physicists have hunted for decades. But even if we have not definitively observed them yet, the theoretical possibility is tantalizing. Several paradoxes suggest the existence of alternatives to black holes. Chief among them is the black hole information paradox. According to quantum mechanics, information cannot be destroyed. But in a classical black hole, any information about the matter that falls in is irretrievably lost to the singularity, violating this sacred principle. Quasi-stable exotic compact objects could offer a solution, by allowing information to be stored and eventually released over vast timescales, rather than annihilated. Another compelling motivation comes from the firewall paradox. Some researchers argue that if information must escape from black holes, then the event horizon cannot be the smooth, benign surface that general relativity predicts. Instead, infalling matter would encounter a firewall of high-energy particles, instantly destroying anything crossing the threshold. Exotic compact objects could sidestep this gruesome fate by lacking true horizons altogether. But what would it feel like to encounter one of these objects up close? Would there be a blinding flash as matter reflects back instead of falling inward? Would we feel tidal forces stretching us into spaghetti strands? Or would the object's internal pressure provide a gentler, though still catastrophic, compression? The possibilities are staggering. The birth of a quasi-stable exotic compact object would itself be a cataclysmic event. Unlike traditional supernovae leading to neutron stars or black holes, the formation might involve bizarre phase transitions, quantum tunneling events, or the creation of entirely new kinds of space-time geometries. The collapse might pause, or bounce, at critical densities, creating ripples and bursts of exotic radiation. Perhaps some gamma-ray bursts we observe are not the deaths of massive stars into black holes, but the births of these exotic objects instead. Looking deeper into their theoretical structure, physicists have explored a mind-bending range of possibilities. Some exotic compact objects might have hard surfaces. Matter falling onto them would crash against the surface, releasing immense energy. Others might have semi-transparent outer layers, absorbing some energy and reflecting some. Some could even have internal cavities, bubbles of different vacuum states suspended within layers of strange matter. The materials composing these objects could be exotic beyond imagination. Quark matter, a hypothetical state where quarks are no longer confined into protons and neutrons, could form the core of some objects. Other proposals involve color superconducting phases, where quark pairs condense similarly to how electrons form Cooper pairs in superconductors, but under far more extreme conditions. Time itself might behave differently near these objects. The extreme gravitational fields would warp spacetime to the brink of forming an event horizon without quite crossing the threshold. To an external observer, processes near the surface might appear to slow almost infinitely. Yet, internally, the object would evolve normally, allowing for complex dynamics invisible to the outside world. This delicate balance between collapse and stability raises profound questions. How finely tuned must the initial conditions be to produce a quasi-stable exotic compact object rather than a black hole? Is their formation rare, requiring exquisitely specific circumstances, or common, hiding among the populations of objects we already attribute to black holes? And if these objects exist, what are their long-term fates? Would they decay slowly by quantum tunneling, leaking mass and energy over trillions of years? Would they eventually collapse into true black holes, or explode violently in exotic supernovae unlike anything ever observed? Could they transition into even stranger forms as the universe evolves? The implications stretch even further. If information can be preserved through quasi-stable exotic compact objects, it opens the door to bizarre theoretical possibilities, like cosmic remnant libraries, where the history of everything that fell into them could, in principle, be retrieved with sufficiently advanced technology. Some speculative theories even suggest that these objects could harbor internal regions much larger than their external size would imply. Pocket universes sealed within microscopic volumes, connected to our space-time only through narrow throats. In a universe populated with such entities, our entire cosmological history might look different. Some supermassive objects at galactic centers, currently assumed to be black holes, might actually be enormous boson stars, gravastars, or other exotic bodies. Their growth, mergers, and interactions could subtly alter galactic evolution. The search for exotic compact objects is one of the most thrilling frontiers in modern astrophysics, blending observational astronomy, theoretical physics, and deep philosophical questions about the nature of reality itself. Every gravitational wave event, every radio signal from a distant quasar, every gamma-ray flash could hold clues, tiny signatures that tell us whether the cosmos harbors these ghostly imposters. But the search is fraught with difficulty. Current instruments can barely scratch the surface of the precision needed. Detecting gravitational wave echoes, for example, requires sifting through noise at levels bordering on the limits of detectability. Differentiating between a black hole and an exotic object requires careful modeling, sophisticated simulations, and immense computational power. Yet hope glimmers on the horizon. Future observatories like LISA, Laser Interferometer Space Antenna, the Einstein Telescope, and Cosmic Explorer promise unprecedented sensitivity. They could reveal not just the crude shapes of space-time ripples, but the fine-grained structure, the fingerprints, of exotic compact objects. The name itself, Quasi-stable exotic compact objects, feels like a riddle wrapped in cosmic mystery. Quasi-stable suggests that they exist in a delicate balance, teetering between survival and collapse. Exotic hints at their unknown, possibly impossible nature, crafted from materials or physics far beyond our current comprehension. Compact objects places them among the densest things in the universe, alongside black holes and neutron stars. But with a critical twist, they defy the final, inescapable singularity that defines a true black hole. To truly grasp the allure and importance of quasi-stable exotic compact objects, or ECOs as some physicists abbreviate them, we must start by challenging everything we think we know about black holes. For decades, black holes have been seen as the inevitable end point for massive stars. When a star several times heavier than our Sun exhausts its nuclear fuel, gravity wins the eternal tug-of-war against outward pressure, and the star collapses under its own weight. According to general relativity, if the mass is sufficient, no known force can stop this collapse, and the star shrinks into a singularity, an infinitely dense point hidden behind an event horizon, a one-way membrane from which nothing, not even light, can escape. But here's the catch: singularities, as described by general relativity, are mathematical artifacts. They're places where the known laws of physics simply break down. In truth, many physicists suspect singularities aren't real objects in nature, but rather indicators that our current theories are incomplete. Enter ECOs, the proposition that instead of forming true singularities, collapsing matter might stabilize into something almost, but not quite, a black hole. A quasi-stable object. A cosmic trickster, hiding just beneath the limits of our perception. Now, what could these exotic objects actually be made of? The possibilities are as staggering as they are strange. Some proposals suggest they could be composed of ultra-dense states of matter far beyond neutron degeneracy pressure, the force that holds up neutron stars. Others hint that new physics could prevent total collapse, invoking quantum effects, hypothetical fields, or entirely new kinds of matter. One thrilling candidate is the boson star. Unlike regular stars made of protons, neutrons, and electrons, all fermions obeying the Pauli exclusion principle, a boson star would be composed of bosons, particles that can occupy the same quantum state without exclusion. This allows them to clump together extraordinarily densely without immediately triggering collapse. Boson stars, if they exist, could be composed of particles like the hypothetical axion, an ultralight particle proposed as a dark matter candidate. If axions form condensates on galactic scales, they could also condense into compact, massive boson stars. A boson star could mimic the gravitational signature of a black hole almost perfectly, but without an event horizon or singularity. Then there are the even wilder ideas. Some theories propose gravastars, gravitational vacuum condensate stars. Instead of a singularity, the collapsing matter undergoes a phase transition, like water freezing into ice, forming a bubble of dark energy at the center. The dark energy exerts a repulsive force, counterbalancing the collapse. The result? From the outside, it would look almost identical to a black hole, but internally, there would be no singularity, just an exotic form of vacuum energy stabilized by its own strange structure. Another candidate? Fuzzballs, emerging from string theory. In this idea, what we call a black hole is actually a tangled, messy ball of strings, the fundamental building blocks of the universe. In the fuzzball model, there is no empty space inside a black hole. Instead, space is filled with this incredibly complex structure of vibrating strings, eliminating the singularity and event horizon entirely. If fuzzballs are real, they could explain many of the paradoxes that plague black hole physics, like the infamous information loss problem. And that brings us to one of the deepest reasons why physicists are hunting for ECOs so feverishly: the black hole information paradox. In simple terms, according to quantum mechanics, information can never be truly destroyed. Yet, according to classical black hole theory, anything that falls into a black hole is lost forever, its information wiped clean when it crosses the event horizon. This contradiction between general relativity and quantum mechanics has been a source of agony and inspiration for generations of physicists. If ECOs exist, if objects can stabilize without true horizons, then maybe information isn't lost after all. Maybe nature has been hiding the answer in plain sight. But how would we detect such elusive objects? After all, black holes themselves are famously hard to observe directly. They emit no light, no radiation, nothing, except via their gravitational influence on nearby matter or through gravitational waves. ECOs would be even more cunning. They could look almost identical to black holes in many cases, making them almost impossible to distinguish through traditional observations. Almost. One promising approach lies in studying gravitational waves, the ripples in spacetime first detected by LIGO in 2015. When two massive objects, like black holes, spiral toward each other and merge, they create a distinctive gravitational wave signal. Crucially, the final stages of this signal, called the ring down, are thought to carry fingerprints of the object's true nature. A true black hole would ring like a perfect bell, its vibrations determined solely by its mass and spin, a concept known as the no-hair theorem. An ECO, however, might have tiny, subtle deviations. Echoes, whispers, imperfections in the dying tones of spacetime itself. Detecting these minute deviations could reveal the presence of something other than a true black hole, a quasi-stable exotic compact object. Already, tantalizing hints have emerged. Some analyses of gravitational wave data have suggested the presence of echoes, faint, delayed signals following the main merger event, consistent with the idea of objects that reflect gravitational waves internally, unlike a pure black hole that absorbs them entirely. These signals are controversial, however, and much more data is needed before any firm conclusions can be drawn. Another path to discovery could lie in the Event Horizon Telescope, the network of radio telescopes that captured the first image of a black hole's shadow in 2019. If ECOs exist, they might create subtly different shadows compared to true black holes, differences that could, in principle, be teased out with more detailed observations. Future generations of the EHT, combined with sophisticated models, could help us peer even deeper into the heart of these cosmic enigmas. Yet for all the excitement, there is also caution. The universe is a ruthless place, and many alternative theories have come and gone, crushed under the weight of new data or more careful analysis. ECOs, for now, remain speculative. Beautiful, thrilling, profoundly important, but speculative. If proven real, they would revolutionize our understanding of gravity, quantum mechanics, and the ultimate fate of matter. If proven false, the journey toward them would still sharpen our tools, refine our theories, and push humanity's cosmic imagination to new heights. And here lies perhaps the most profound implication. The search for quasi-stable exotic compact objects is not just a scientific quest. It is a philosophical one. It forces us to confront the limits of knowledge itself. What does it mean to know something about an object we can never touch, never see directly? How do we uncover truths hidden behind the very fabric of reality? And if the universe does indeed permit these strange, resilient, unthinkable structures, what else might it permit? What other marvels might be waiting, just beyond the edges of our comprehension, whispering to those daring enough to listen? In the coming years, as gravitational wave astronomy matures, as new telescopes probe the skies with ever-increasing precision, and as theoretical physicists push the boundaries of known physics, the true nature of these elusive cosmic phantoms may finally be revealed. Whether they prove to be real or not, the pursuit of quasi-stable exotic compact objects will continue to ignite our deepest curiosity, challenging our assumptions and expanding the horizons of what is possible. Because at the edge of everything, at the threshold between known and unknown, the universe still holds secrets that even our wildest theories can barely contain. But here's the catch: singularities, as described by general relativity, are mathematical artifacts. They're places where the known laws of physics simply break down, yielding infinities that make no physical sense. Many physicists quietly accept that singularities are signs that our theories are incomplete. In other words, singularities might not really exist in nature. They might be telling us that at extreme conditions, something else happens, something that doesn't lead to infinite densities and the destruction of space-time itself. Enter quasi-stable exotic compact objects. These are theoretical structures that could form instead of black holes when massive stars die. They could mimic the external appearance of a black hole so perfectly that even the most sensitive telescopes might be fooled. And yet, inside, they would harbor no singularity, no event horizon, and perhaps even no catastrophic fate for anything falling into them. They might be made of exotic states of matter that resist total collapse. They might pulse, oscillate, slowly leak energy, or even evolve over unimaginable timescales. Some theories suggest they could last longer than the observable universe itself. But what could they be made of? That question is one of the greatest unsolved mysteries in modern theoretical physics. Some hypotheses propose that ECOs could be constructed from ultra-dense forms of matter, like boson condensates, states where particles called bosons collapse into a single quantum state, behaving like a gigantic atom. Others suggest exotic fields, like scalar fields that saturate space in a way normal matter never could. There's even speculation that ECOs might be relics from the earliest moments after the Big Bang, frozen echoes of a time when the universe was a hot, chaotic stew of unknown particles and energies. Imagine, for a moment, a black hole twin made not of collapsing baryonic matter, but of pure quantum fields, structured in such a way that gravity almost, but not quite, wins. Picture a cosmic object that looks like a black hole from a distance, bending light, distorting time. But when you approach close enough, you find no event horizon, no point of no return. Instead, you might encounter a strange surface, a fuzzy region where space-time itself becomes a roiling sea of quantum fluctuations, barely holding itself together against gravitational collapse. The reason we haven't definitively detected ECOs yet is because, by design, they could be almost indistinguishable from black holes. Gravitational waves, ripples in space-time caused by violent cosmic events, have given us a new tool for probing the nature of compact objects. When two black holes merge, they emit gravitational waves that ring like a bell, a process called the ring-down. If the final object is a perfect black hole, the ring-down follows a very precise pattern. But if it's an ECO, the ring-down could carry subtle deviations, tiny echoes or alterations that hint at a different internal structure. Physicists are now meticulously analyzing gravitational wave signals from detectors like LIGO and Virgo, hunting for these elusive signatures. So far, the data mostly aligns with the predictions for black holes, but there are whispers in the noise, tiny hints, statistical anomalies that have fueled intense debate. Are we seeing the first signs of ECOs? Or are these just artifacts of imperfect measurements? The answer remains tantalizingly out of reach. The possibilities are staggering. If ECOs exist, they could reshape our understanding of the ultimate fate of matter. Black holes, as currently understood, eventually evaporate through a process called Hawking radiation, a slow trickle of particles escaping from near the event horizon, caused by quantum effects. Over unimaginably long timescales, black holes shrink and disappear. But if an object has no event horizon, if it is quasi-stable rather than fully collapsed, its end might look very different. It might decay slowly, leaking radiation at a different rate. It might fluctuate, pulse, or even stabilize indefinitely. In a universe headed toward cold, dark emptiness, the so-called heat death, ECOs could be among the very last structures still persisting, tiny flickers of complexity in a sea of decay. There's also the haunting possibility that what we call black holes today, the supermassive monsters at the centers of galaxies, the stellar mass objects scattered through the Milky Way, might actually be a mix. Some could be true black holes, others quasi-stable ECOs, and we simply haven't had the tools to tell the difference yet. If that's true, then every gravitational wave detection, every observation of a shadowy object at the heart of a galaxy, becomes a potential clue, a piece of a puzzle far grander than we realized. Consider the types of ECOs that have been proposed: gravastars, boson stars, fuzzballs, and other more speculative structures. Gravastars, short for gravitational vacuum stars, are objects where a thin shell of ultradense matter surrounds a bubble of dark energy, a repulsive force that prevents collapse. Boson stars, on the other hand, are composed entirely of bosonic particles, forming a quantum superfluid that resists gravitational pressure without the need for degeneracy pressure, like in neutron stars. Fuzzballs arise from string theory and propose that black holes are really tangled webs of strings, with no traditional event horizon or singularity at all. Each of these models offers a radically different vision of what an ECO might be, each more mind-bending than the last. And the truly astonishing part? Some versions of ECOs could allow information to escape. In black hole physics, one of the greatest unsolved puzzles is the information paradox. If things fall into a black hole and the black hole eventually evaporates, where does the information go? According to quantum mechanics, information cannot simply be destroyed. Yet in the standard black hole model, there's no clear mechanism for its preservation. ECOs might offer an escape hatch. Without a true event horizon, information might not be lost at all, but simply delayed, scrambled, and eventually released in subtle, complex patterns. Think about that for a moment. ECOs might not just save physics from paradoxes, they might also hint at entirely new realms of quantum gravity, places where the union of general relativity and quantum mechanics becomes not a distant dream, but an observable reality. They might be the laboratories of nature's deepest secrets, hiding in plain sight among the stars. As we push deeper into the mystery, we also confront profound philosophical questions. What does it mean for an object to have no true boundary? If the cosmos creates structures that mimic black holes without truly being black holes, what else might exist out there, hiding behind the veil of our limited senses? Could there be a zoo of exotic objects, each more bizarre than the last, waiting to be discovered? Are ECOs the missing link between the macroscopic world of relativity and the microscopic dance of quantum fields? These are not idle speculations. Major scientific collaborations are already proposing next-generation observatories, more sensitive gravitational wave detectors, space-based interferometers like LISA, and ultra-precise radio telescopes, designed specifically to hunt for signs of ECOs. The discovery of even a single confirmed quasi-stable exotic compact object would revolutionize physics overnight, forcing textbooks to be rewritten and opening new frontiers for exploration. And yet, the story might be even stranger than it first appears. Some models suggest that ECOs could be dynamic entities, changing over time. Instead of static, eternal objects, they could undergo internal phase transitions, shifting between different exotic states, shedding energy or mass in the process. In some scenarios, an ECO might start as a nearly indistinguishable black hole mimic, but over millions or billions of years, evolve into something utterly unrecognizable, a shimmering, oscillating entity broadcasting subtle signals across the cosmos. If that is the case, then ECOs are not just passive relics of stellar death, they are active players in the cosmic story, capable of influencing their surroundings, triggering high-energy events, or even seeding new structures in space. Their presence might explain certain astrophysical phenomena we currently struggle to understand, mysterious gamma-ray bursts, unexplained cosmic radio flashes, or even some forms of dark matter clumping. And speaking of dark matter, some scientists speculate that a population of primordial ECOs, born not from stars, but from quantum fluctuations in the early universe, could make up a portion of the elusive dark matter itself. If that's true, then by studying ECOs, we could be unlocking not just the mystery of compact objects, but the very nature of the invisible scaffolding that holds galaxies together. The stakes could not be higher. The search for quasi-stable exotic compact objects is not just about classifying strange new celestial bodies. It's about testing the limits of our most fundamental theories. It's about finding out whether the universe plays fair with the rules we've discovered so far, or whether it hides secret laws, stranger and deeper, that we are only beginning to glimpse. And yet, despite the immense challenges, the chase continues. Every new gravitational wave detection, every improvement in telescope resolution, every theoretical breakthrough brings us closer to an answer. Are we on the verge of discovering that the universe is filled not with simple black holes, but with a dazzling menagerie of exotic, quasi-stable wonders? Or will the echoes fade, leaving only silence, and black holes triumphant? The story of quasi-stable exotic compact objects is a story of humility and wonder, a reminder that the universe is not obligated to be simple or understandable. It is vast, ancient, and profoundly creative. And somewhere out there, in the dark spaces between the stars, it may be quietly rewriting the laws we thought were absolute. But what could they be made of? This question cracks open a vault of staggering possibilities. Some models propose that quasi-stable exotic compact objects are composed of ultra-dense forms of matter beyond anything we have ever witnessed. Strange quark matter, for instance, a hypothetical ultra-stable state where up, down, and strange quarks are blended into a perfectly dense soup, could form a type of object more stable than neutron stars, yet not collapsing into a black hole. These so-called strange stars could hover on the very brink of gravitational collapse, radiating almost no light, hiding perfectly among the cosmos' darkest shadows. Other proposals are even wilder. Some physicists theorize about boson stars, made entirely of bosons, particles that don't obey the Pauli exclusion principle, meaning they can all occupy the same quantum state. Unlike fermions, which build up the layers of matter we experience daily, bosons could condense into a single, gigantic quantum state on a cosmic scale. A boson star would be invisible in ordinary light, potentially held together by quantum mechanical effects and self-interaction, balancing on the knife edge between stability and implosion. And then there are the gravastars, perhaps the most radical idea of them all. Instead of forming a singularity, the gravitational collapse of a massive star could cause a phase transition of space-time itself. In this vision, the core of the dying star would not continue collapsing inward indefinitely but would undergo a kind of cosmic metamorphosis, forming a bubble of dark energy, the mysterious force accelerating the expansion of the universe, surrounded by a thin, ultra-dense shell of ordinary matter. From the outside, a gravastar could appear indistinguishable from a black hole. Yet no singularity, no event horizon, and no information loss would exist within. Each of these possibilities, while fantastical, are rooted in rigorous attempts to resolve the deep paradoxes surrounding black holes, especially the black hole information paradox, one of the greatest unsolved problems in theoretical physics. According to quantum mechanics, information about the physical state of a system cannot be destroyed. But if a black hole evaporates through Hawking radiation and the information about whatever fell in is lost, quantum theory would be violated. Quasi-stable exotic compact objects offer an elegant way out. If there's no true event horizon, information might not be lost after all. If such objects exist, they might very well populate the universe in large numbers, masquerading as black holes in the heart of galaxies, drifting invisibly through interstellar space, or quietly lurking in dark regions beyond the reach of our best instruments. They might even be responsible for some of the most mysterious astrophysical phenomena we observe, such as certain gravitational wave signals that don't quite match black hole mergers, or the enigmatic fast radio bursts that seem to blink from the cosmos with no obvious source. The mind-bending part is that detecting the difference between a true black hole and a quasi-stable exotic compact object could be incredibly difficult. From afar, they warp space-time almost identically. Light bends around them in nearly the same way, and objects orbiting them behave nearly identically. But small differences, nearly imperceptible ripples in the fabric of space-time, could give them away. Tiny echoes in gravitational wave signals, minute deviations in the motion of nearby stars, or subtle patterns in electromagnetic emissions could be the telltale signs that we are not dealing with black holes at all, but with something far stranger. Imagine an ECO slightly larger than its Schwarzschild radius, the theoretical size of a black hole's event horizon. Light could orbit around it multiple times before escaping, creating bizarre and distorted images of the surrounding universe. A spacecraft approaching such an object might find itself caught in a gravitational funhouse, where directions twist upon themselves and time seems to stretch to infinity without ever quite snapping. And what would it feel like to fall into one? Unlike a true black hole, where crossing the event horizon seals your fate with no hope of return, an ECO might allow a voyager to survive, at least for a while. As you fell closer, you might experience extreme gravitational tides, bizarre time dilation effects, and intense radiation fields. Yet, without an event horizon, there would theoretically be a way back, although the path might be more treacherous than any journey imaginable. Some theories even suggest that ECOs could evolve over time, gradually leaking their energy through mechanisms like Hawking-like radiation or quantum tunneling effects. Over billions upon billions of years, they could shrink, change phase, or even evaporate completely, leaving behind nothing but a faint whisper in the cosmic background. The creation of such objects could trace back to the earliest moments after the Big Bang. In the chaotic, high-energy environment of the infant universe, exotic states of matter could have formed and frozen into quasi-stable configurations. If so, ECOs might be relics of the primordial universe, still roaming the cosmos today, carrying information about epochs otherwise lost to time. The diversity of possible ECO models is astonishing. Some predict that they could be almost perfectly stable, with lifetimes longer than the current age of the universe by many orders of magnitude. Others suggest that they could be metastable, lasting for eons but ultimately destined to decay. Still others propose that they could occasionally undergo catastrophic transitions, releasing titanic bursts of energy that could seed galaxies or even trigger new cosmic phenomena. One of the tantalizing aspects of ECOs is their potential link to dark matter, the mysterious substance that makes up most of the universe's mass but has never been directly observed. Some scientists speculate that dark matter might consist, at least in part, of tiny, ancient ECOs, perhaps primordial black hole-like objects that never quite formed true black holes. If so, studying ECOs could finally unlock the secrets of dark matter, reshaping our understanding of the universe at the most fundamental level. And yet, despite the beauty and elegance of these theories, the search for ECOs remains on the razor's edge between speculation and discovery. With the advent of gravitational wave astronomy, we now have tools capable of probing the extreme conditions near compact objects with unprecedented precision. Observations from LIGO, Virgo, and future detectors like LISA could reveal the subtle signatures of ECOs hidden in the data, the faint echoes following a merger, the tiny deviations from expected black hole behavior, the whispers of exotic matter beyond the reach of conventional stars. Each new detection pushes us closer to an answer. If we find even a single object that deviates from the black hole paradigm, it would be a revolutionary moment, forcing a fundamental rethinking of gravity, quantum mechanics, and the ultimate fate of matter and information in the universe. It would mean that nature, as always, is more imaginative than we dared to believe. Even now, theorists are hard at work modeling every possible ECO candidate, calculating how they would interact with light, how they would merge, how they would evolve, and what kinds of signals they would produce. Some models involve additional dimensions of space, exotic fields permeating the cosmos, or new forces of nature entirely. Each possibility opens new avenues for discovery, and new mysteries to unravel. Yet the possibility remains that ECOs might forever elude direct detection, blending seamlessly with the population of black holes, hiding in plain sight, their secrets locked away behind a veil of near-perfect mimicry. In that case, the pursuit itself becomes the story, a testament to human curiosity, imagination, and the relentless drive to understand the universe in all its strangeness. This new phase could be an exotic form of vacuum energy, a region of space-time governed by a different set of physical laws. Instead of continuing to collapse into a singularity, the core would stabilize, supported by the pressure of this vacuum energy. The outer layers would remain suspended just beyond what would traditionally be the event horizon, creating a shell that preserves the object's mass and gravitational influence without allowing true collapse. From a distance, a gravistar would be almost identical to a black hole. It would bend light with immense gravity, distort time itself, and trap anything that ventured too close. Yet, crucially, it would lack the defining features of a true black hole. There would be no singularity crushing matter to infinite density, and no point of no return where information is irretrievably lost. The existence of such objects would solve many paradoxes that black holes create, especially the infamous information paradox. In traditional black hole theory, anything that crosses the event horizon is forever lost, erasing information in a way that quantum mechanics claims is impossible. Gravistars, and other exotic compact objects, offer a loophole. If there is no true event horizon, then information could, in theory, still escape, albeit slowly, perhaps encoded in subtle radiation or structural vibrations of the object itself. But the mystery deepens even further. Some theories push beyond gravistars and boson stars to consider that exotic compact objects could be built from entirely new forms of matter, predicted by speculative extensions of the standard model of particle physics. Objects like cue balls, for instance, would be composed of stable configurations of scalar fields, fields that pervade space and time. These fields could clump together into massive, stable structures capable of resisting gravitational collapse. Cue balls could be so dark, so inert, and so similar to black holes in their gravitational footprint that they might have been hiding among us all along, camouflaged within the deep voids of space. The very possibility of these quasi-stable exotic compact objects reshapes how we think about death and survival on a cosmic scale. Traditional black holes are seen as the ultimate tombs. Matter and energy fall into them and are lost forever, their mass contributing only to the growing, featureless darkness. ECOs, however, hint at survival, at transformation. They suggest that even in the universe's most extreme environments, complexity, structure, and perhaps even information itself can endure. Detecting these enigmatic objects, however, is an immense challenge. Because they mimic black holes so closely, distinguishing between a black hole and an ECO requires looking for tiny deviations in behavior. Scientists suggest that one way to spot them might be through gravitational waves, ripples in space-time caused by massive objects colliding or vibrating. When two black holes merge, the resulting gravitational wave signal has a very specific form, a violent burst, followed by a predictable, ring-down, phase as the new black hole settles. If instead two ECOs merged, the ring-down might include unexpected echoes, faint, delayed ripples that bounce back and forth inside the object's structure, leaking out over time. These echoes would be a cosmic whisper hinting that the object has an internal surface rather than an event horizon. Some studies have even claimed tentative evidence for such echoes in the data from LIGO and Virgo, the world's premier gravitational wave detectors. These hints are controversial, fiercely debated within the astrophysical community, but they have ignited a firestorm of interest. If confirmed, they would be nothing less than a revolution in our understanding of the universe. Beyond gravitational waves, other possible clues could come from the way matter interacts near the edge of these objects. Infalling material around a true black hole disappears completely once it crosses the event horizon. Around an ECO, however, some matter might reflect off the surface or be absorbed differently, creating subtle differences in the emitted radiation. Future observatories, with greater sensitivity across the electromagnetic spectrum, might be able to tease out these differences, unveiling the true identity of some of the universe's darkest objects. Yet for all the theoretical possibilities, one haunting question looms: why would the universe produce ECOs at all? Why would nature favor such intricate, delicate objects over the brutally simple singularity of a black hole? Some physicists believe the answer lies in quantum gravity, the still mysterious theory that would unify general relativity and quantum mechanics. Near the Planck scale, where energies and densities reach unimaginable levels, space-time itself could become quantized, granular, resistant to infinite compression. Black hole singularities might be impossible because space-time refuses to allow them. ECOs, then, would be the natural outcome, the universe's way of respecting the ultimate limits imposed by quantum laws. Others suggest that the early universe might have seeded exotic compact objects in vast numbers. During the first fractions of a second after the Big Bang, when temperatures and energies were inconceivably high, phase transitions in the cosmic fields could have created stable pockets of exotic matter. These primordial ECOs could have survived until today, hidden within the great voids between galaxies, acting as invisible scaffolding for cosmic structure, and perhaps even constituting a portion of the elusive dark matter that outweighs all visible stars and galaxies combined. The idea that ECOs might contribute to dark matter is particularly tantalizing. Dark matter is known only through its gravitational effects, bending light from distant galaxies, shaping the rotation curves of galaxies, and influencing the large-scale structure of the universe. If some fraction of dark matter consists of exotic compact objects, it would explain why it interacts so little with ordinary matter and radiation. Detecting such dark ECOs would require not just looking at where light is absent, but carefully analyzing gravitational microlensing events, subtle deflections of starlight caused by invisible massive bodies drifting across the sky. The possibility that dark matter could be composed of countless quasi-stable exotic compact objects opens up a new frontier in the search for the universe's missing mass. It hints that the cosmos could be teeming with unseen relics of ancient processes, still lurking in the shadows, influencing the fates of galaxies and the evolution of cosmic history without ever revealing themselves to our primitive telescopes. Theoretical physics continues to spin new possibilities, driven by the hope that somewhere, somehow, evidence for ECOs will emerge clearly. Proposals range from more refined gravitational wave observations to next-generation radio telescopes that might pick up telltale signs from matter interacting with exotic surfaces. Some even suggest that ECOs could reveal themselves through their interaction with black holes themselves, if a black hole were to consume an ECO and produce unexpected gravitational wave signatures. The implications of discovering even a single quasi-stable exotic compact object would be staggering. It would confirm that singularities do not exist, overturning a century of black hole physics. It would validate new states of matter, new forms of space-time, and possibly new laws of physics beyond anything imagined. It might even provide the first concrete clues toward a quantum theory of gravity, the holy grail of modern theoretical physics. And yet, for now, ECOs remain tantalizing phantoms, lurking in theory, hinted at by data, but not yet fully grasped. They embody the essence of scientific mystery, the possibility that the universe holds structures and phenomena so strange, so outside ordinary experience, that even naming them feels like an act of daring imagination. Each of these models, strange stars, boson stars, gravistars, fuzzballs, points toward a deeper truth. Our understanding of gravity, matter, and space-time is still woefully incomplete. Exotic compact objects might be telling us that at the very edge of physics, the universe plays by different rules, ones that general relativity alone cannot fully describe. If these objects exist, they would not just be curiosities scattered through the cosmos. They would be profound laboratories of nature, whispering secrets about quantum gravity, about the unification of forces, and perhaps even about the true origin of the universe itself. Detecting these elusive entities, however, is a monumental challenge. To the untrained observer, and even to our most advanced observatories, a quasi-stable exotic compact object could appear almost identical to a black hole. Its immense gravity would curve space-time, lens light, and create shadows similar to those captured by projects like the Event Horizon Telescope. Yet subtle differences might exist. For instance, if the object lacks a true event horizon, matter falling onto its surface would behave differently. Instead of vanishing without a trace, infalling material might crash onto a physical surface, releasing a burst of energy, or it might create slight echoes detectable in gravitational waves. Gravitational wave astronomy, a field still in its infancy, could be the key to uncovering these cosmic imposters. When two massive objects collide and merge, they emit ripples in spacetime, gravitational waves, that can be detected here on Earth. The pattern of these waves, the so-called ring-down phase after the merger, is especially sensitive to the properties of the final object. A true black hole would produce a clean, predictable signal, fading away in a precise manner. A quasi-stable exotic compact object, by contrast, might produce tiny deviations, delayed echoes, unexpected frequencies, slight prolongations of the signal, that betray its exotic nature. Already, some physicists have claimed tentative hints of such echoes in the data from the LIGO and Virgo observatories. These claims remain controversial and unconfirmed, but they ignite a thrilling possibility that within the gravitational songs of colliding giants, we are hearing whispers of new physics. Theoretical physicists are racing ahead, developing detailed models of how these echoes would arise and how different types of exotic objects would produce distinct signatures. Each candidate, whether a gravistar, a boson star, or a fuzzball, would leave its own fingerprint on the waves of spacetime. Future generations of gravitational wave detectors, more sensitive and finely tuned, might finally allow us to distinguish between a true black hole and one of its exotic cousins. Beyond gravitational waves, other avenues exist. High-energy observations of accretion disks, the swirling matter spiraling into these objects, could provide clues. In a traditional black hole, the innermost stable circular orbit defines how close material can orbit before plunging past the event horizon. If exotic compact objects lack a true horizon, they might allow material to orbit even closer or behave in ways subtly different from expectations. The precise spectra of X-ray emissions, the timing of bursts, and the structure of surrounding jets could all carry hidden messages waiting to be decoded. Another tantalizing clue could come from observing the object's stability over cosmic timescales. Black holes are thought to be perfectly stable except for the almost undetectable trickle of Hawking radiation over trillions of years. Exotic compact objects, being only quasi-stable, might exhibit slow evolution, gradual leakage of mass, or even occasional catastrophic transformations. Watching a seemingly inert cosmic shadow suddenly burst with energy, or change shape could be the telltale signature that we are looking not at a black hole, but at something profoundly stranger. Yet for all these possibilities, a sobering reality remains: the universe does not yield its deepest secrets easily. Noise, distance, and cosmic clutter conspire to blur the signals we seek. Separating the faint footprints of exotic physics from the roar of the cosmos demands not only better instruments, but also a revolution in how we think about data, patterns, and probability. Still, the hunt continues, fueled by the almost unbearable promise that hidden among the billions of stars and the blackened hearts of galaxies, there exist objects so bizarre that they defy every expectation, objects that hint at new realms of reality just beyond our grasp. If quasi-stable exotic compact objects are real, they could solve puzzles far beyond the scope of astrophysics alone. They could illuminate the true nature of spacetime at the Planck scale, where quantum mechanics and gravity must merge. They could reveal whether information is truly preserved in all physical processes, or whether some cosmic censorship still veils ultimate truths. They could even offer pathways toward new technologies, based on a deeper understanding of gravity, matter, and energy. At their core, these objects challenge the idea that death, even cosmic death, is absolute. In the standard picture, a star's collapse leads inevitably to a final, featureless black hole, a kind of cosmic tombstone. But if instead collapse leads to a quasi-stable exotic object, then death itself becomes more complicated, more interesting, more alive with possibilities. Rather than an end, it could be a transformation, a doorway into realms of physics that have so far existed only in the minds of theorists and the dreams of visionaries. The quest for understanding these objects also forces us to confront the limits of our theories. General relativity, magnificent as it is, cannot be the final word, because it predicts its own breakdown at singularities. Quantum mechanics, with all its successes, has yet to explain gravity. Somewhere between these two pillars, a deeper theory must exist, and exotic compact objects could be the stepping stones that guide us there. Even the terminology hints at our uncertainty. Quasi-stable implies that they might not last forever, that they teeter on a precarious balance. Over unimaginable stretches of time, they might decay, transform, or reveal deeper layers of structure. Their stability could be an illusion, a temporary phase in a cosmic drama playing out over eons. The word, exotic, reminds us that these objects lie outside the familiar. They are not merely strange by degree, like a hotter star or a denser planet. They are strange by kind, embodying states of matter and spacetime that have no counterpart in our everyday experience. And compact object places them in a lineage, with white dwarfs, neutron stars, black holes, but also sets them apart. They are compact, yes, but their compactness harbors mystery rather than finality, complexity rather than simplicity. The very act of contemplating quasi-stable exotic compact objects expands our imagination. It forces us to envision matter behaving in ways we have never seen, forces acting in manners we have never measured, and space-time itself twisting into configurations we have barely begun to imagine. It asks a deeper question: what else might the universe be hiding, just beyond the veil of our current understanding? Gravitational wave astronomy, a field still in its infancy, could be the key to unlocking the mysteries of these objects. When massive bodies like neutron stars or black holes merge, they produce ripples in space-time itself, gravitational waves that race across the cosmos at the speed of light. These waves carry with them the imprint of the objects that created them. By studying the precise pattern of these waves, scientists can infer not just the mass and spin of the colliding objects, but also their internal structures and physical natures. If two black holes merge, the gravitational waves they emit should have a specific, predictable signature. But if the merging bodies are exotic compact objects instead, the signal could differ in subtle but crucial ways. Perhaps there would be echoes, faint repetitions of the original signal caused by vibrations of a physical surface instead of an endless plunge into a singularity. Perhaps the ring-down phase, the final, dying tones of the gravitational wave signal, would deviate from the patterns predicted by classical general relativity. Detecting such deviations would not merely confirm the existence of exotic compact objects, it would revolutionize our understanding of physics at the most fundamental level. Current gravitational wave detectors like LIGO and Virgo are already sensitive enough to tease out some of these differences, though no clear evidence has yet been found. Future observatories, such as the Laser Interferometer Space Antenna, LISA, and the Einstein telescope, will have even greater sensitivity. These instruments could provide the first definitive proof that the cosmos contains more than black holes and neutron stars, that somewhere out there, quasi-stable exotic compact objects silently await discovery. Yet another avenue of investigation lies in the behavior of light around these objects. A traditional black hole bends light around it so severely that it creates a shadow, a dark, roughly circular region surrounded by a bright ring, as famously imaged in the case of the supermassive black hole at the center of galaxy M87. An exotic compact object, lacking a true event horizon, might produce a shadow that looks slightly different. The brightness, sharpness, or symmetry of the surrounding ring could vary in ways that betray the object's true nature. Moreover, if the object has a surface instead of an event horizon, infalling matter might emit flashes of radiation upon impact. These flashes could, in principle, be detected by X-ray telescopes or radio observatories. So far, no such signals have been definitively observed, but the universe is vast, and our exploration has only just begun. Theoretical physicists are also hard at work refining the models that predict these phenomena. Some argue that exotic compact objects could oscillate or vibrate in unique ways, producing characteristic frequencies that could be detected in electromagnetic or gravitational signals. Others suggest that these objects might slowly leak energy over cosmological timescales, perhaps explaining certain mysterious observations, such as unexplained gamma-ray bursts or the excess of high-energy cosmic rays. The stakes are extraordinarily high. If even one quasi-stable exotic compact object is detected, it would force a major revision of general relativity, one of the most successful theories in scientific history. It would provide direct evidence that quantum effects play a crucial role in the behavior of gravity, even outside the realm of the infinitesimally small. It might offer the first glimpse of a successful theory of quantum gravity, the long-sought unification of Einstein's geometric vision of spacetime with the probabilistic world of quantum mechanics. The implications extend even further. Understanding these objects could shed light on the earliest moments of the universe itself. Some cosmological models suggest that during the Big Bang, regions of exceptionally high density could have formed primordial exotic compact objects, which might still be floating through space today. Detecting them would offer a direct window into the first fractions of a second after creation, a view into a time otherwise shrouded in mystery. Furthermore, quasi-stable exotic compact objects could be candidates for dark matter, the invisible substance that outweighs ordinary matter 5-1 but has so far defied all attempts at direct detection. If these objects are numerous enough and massive enough, they could account for a significant portion of the missing mass of the universe. Searching for them, then, is not just a matter of academic curiosity. It is a quest to solve one of the deepest mysteries in all of science. In contemplating these possibilities, we are forced to confront the very limits of human knowledge. The universe is not obligated to conform to our expectations or to fit neatly within the theories we construct. Time and again, nature has surprised us, revealing layers of complexity and wonder that we had not anticipated. Quasi-stable exotic compact objects represent a new frontier, a challenge to our imagination, and a call to expand our understanding beyond the comfortable frameworks of the past. The journey toward discovering these objects will demand not just technological innovation but philosophical resilience. It requires us to admit that even our most celebrated theories might be incomplete, that the final word on gravity, space-time, and the fabric of reality has not yet been written. It demands an openness to the strange, the exotic, and the unknown. Already, young physicists and visionary researchers are drawing inspiration from the possibility of exotic compact objects. They are designing new detectors, proposing novel experiments, and developing ever more sophisticated simulations to explore the subtle clues that might distinguish these objects from ordinary black holes. They are questioning long-held assumptions, re-examining the fundamental principles that underlie our models of the cosmos. Perhaps, in some quiet corner of the universe, a quasi-stable exotic compact object is waiting for us to find it. Perhaps it will appear first as a faint echo in a gravitational wave, a tiny asymmetry in a black hole's shadow, or an unexplained burst of radiation from the depths of space. Perhaps, even now, the signals are already arriving at Earth, woven into the data we are only beginning to understand. The future promises deeper revelations still. As our instruments grow more sensitive and our theories grow more refined, the dream of uncovering these hidden structures becomes ever more plausible. With each passing year, we inch closer to a moment when one of humanity's greatest adventures, the quest to understand the most extreme and enigmatic objects in the universe, reaches a new and extraordinary chapter. As humanity presses forward into the depths of the unknown, we are reaching the limits of what current physics can explain. The existence of quasi-stable exotic compact objects could challenge everything we know about black holes, neutron stars, and the nature of gravity itself. These mysterious objects, which straddle the line between conventional matter and the deep mysteries of quantum physics, force us to rethink some of the most fundamental principles of our universe. For decades, we have adhered to the concept of a black hole as an object with an event horizon, beyond which not even light can escape. But what if this is not the whole picture? What if some of these objects have surfaces or structures that allow for interaction with matter, light, and gravity in ways that were previously thought impossible? The potential discovery of these quasi-stable exotic compact objects would not just alter our understanding of the extreme conditions around stellar remnants. It could redefine the very foundations of modern physics. For example, if these objects truly have a surface or a boundary, they would challenge the classical understanding of singularities and event horizons. The so-called information paradox that surrounds black holes, the puzzle of what happens to information that falls into a black hole, could find new resolution if these exotic objects somehow preserve information in ways that black holes cannot. These objects could also provide the first clues about the elusive quest for a unified theory of quantum gravity. General relativity and quantum mechanics have long been at odds with each other, and understanding exotic compact objects could offer a bridge between these two pillars of modern physics. By studying the behavior of light and matter around these objects, we could gain critical insights into how the quantum nature of space-time operates in the most extreme environments, where the classical laws of physics break down. But the discovery of these objects won't be easy. Scientists are already pushing the limits of our observational tools, with gravitational wave detectors like LIGO and Virgo, and electromagnetic observatories like the Event Horizon Telescope, offering glimpses into the mysterious corners of the universe. However, the signals emitted by quasi-stable exotic compact objects could be subtle and easily masked by other astrophysical phenomena, such as black hole mergers or neutron-star collisions. In many ways, these objects may remain hidden in plain sight, just beyond the reach of our current instruments, waiting for the next leap in technology to reveal them. One of the most exciting possibilities for detecting these objects lies in the study of gravitational waves. These ripples in spacetime, caused by the acceleration of massive objects like merging black holes or neutron stars, carry critical information about the nature of the objects that created them. As we push the sensitivity of gravitational wave detectors, we may begin to notice small anomalies in the waveforms that hint at the presence of exotic compact objects. Perhaps the ring-down phase of a gravitational wave, for example, could reveal a subtle difference if the object involved is not a black hole, but something even stranger. Similarly, the study of light, particularly in the X-ray and gamma-ray spectra, may offer another window into the secrets of quasi-stable exotic compact objects. If these objects do indeed have a surface, or a structure that allows matter to interact with them in ways that traditional black holes cannot, we could expect to see unusual patterns of radiation. For instance, the accretion disks around these objects may behave differently than those surrounding black holes, emitting radiation in a way that is not yet understood. This opens up a tantalizing possibility. We might already be detecting these objects without realizing it. High-energy astrophysical phenomena, such as gamma-ray bursts or mysterious high-energy cosmic rays, might be the result of interactions with exotic compact objects. These strange emissions could be the first hints that we are dealing with a different class of objects entirely, one that operates under a new set of physical laws. In the long term, the study of quasi-stable exotic compact objects could have profound implications for cosmology. Our understanding of the formation and evolution of galaxies, stars, and black holes may need to be revised if these objects play a larger role in the universe than we currently imagine. They could offer new insights into the earliest moments of the universe, when the first stellar remnants were born. And they might even provide answers to some of the biggest questions in astrophysics, such as the nature of dark matter, or the fate of the universe itself. For now, the search continues. As we refine our observational tools and improve our understanding of the universe's most extreme environments, we may one day find ourselves staring directly at one of these enigmatic objects. The day we finally discover the true nature of quasi-stable exotic compact objects will mark a monumental shift in our understanding of the cosmos. It will be a moment of profound revelation, not just about the objects themselves, but about the very nature of the universe we inhabit. In many ways, the story of quasi-stable exotic compact objects is still just beginning. What we know so far is tantalizing, but the true nature of these objects remains one of the most exciting and mysterious frontiers in modern astrophysics. With each new discovery, we edge closer to understanding the deepest secrets of the universe. And when the day finally comes that we can conclusively identify one of these strange, elusive objects, it will be a moment of scientific triumph, a testament to humanity's enduring curiosity and our relentless drive to understand the mysteries of the cosmos. As we dive deeper into the nature of quasi-stable exotic compact objects, the pursuit of understanding their properties becomes even more crucial. These objects, standing at the intersection of established theory and the unknown, challenge the boundaries of classical physics, especially when considering the nature of space, time, and matter in extreme environments. One of the central questions that arise when thinking about these objects is how they form, and how we might recognize their presence in the universe. In the case of black holes, we understand that they form from the collapse of massive stars, whose internal pressure can no longer counteract the force of gravity. This collapse leads to the formation of a singularity, where density becomes infinite, and the laws of physics as we know them break down. But with quasi-stable exotic compact objects, the formation process is more elusive. These objects might not require a collapse to a singularity, and they could involve more complex physical processes at their core, ones that would require us to develop new models of stellar evolution. Could these objects form in a way that is fundamentally different from the process that produces black holes? One possibility is that they might arise from the collapse of very specific types of massive stars that undergo unusual stages of compression, allowing exotic matter to stabilize into these unique compact forms. This would imply that these objects could potentially be formed during the later stages of stellar evolution, or in environments with extreme magnetic or gravitational fields. It also suggests that their formation might be rarer or more localized, depending on the specific conditions required. Moreover, the idea that quasi-stable exotic compact objects may involve some form of exotic matter brings up important questions about the nature of matter itself. In traditional physics, matter is composed of baryons, particles like protons and neutrons, which are governed by the strong nuclear force. However, exotic matter goes beyond this simple description. It could involve particles that do not fit into the standard model of particle physics, like hypothetical bosonic particles, or even entirely new forms of matter that we have not yet observed. This kind of exotic matter could be the key to understanding the stability of these objects. In typical black holes, matter collapses into a singularity, where it is thought to be lost to the universe, with no way to recover information about it. But with quasi-stable exotic compact objects, the presence of this exotic matter might allow for new behaviors that don't involve the total destruction of information. This could be tied to the information paradox mentioned earlier. If these objects preserve the information of the matter that falls into them, they could provide new insights into how quantum mechanics and gravity could work together. As we think about how we might detect these objects, it is worth considering the variety of astrophysical signals they might emit. Traditional black holes, when they interact with their surroundings, produce highly energetic phenomena like X-ray emissions and gravitational waves, which we can use to detect their presence. But these exotic compact objects could produce different signatures. The way they interact with surrounding material could lead to a different pattern of radiation, potentially detectable through electromagnetic waves or high-energy cosmic rays. Perhaps they would emit unusual spectral lines that differ from the patterns we see in black hole accretion disks or the jets emitted by black holes. Additionally, the gravitational waves produced by the mergers of these exotic objects could have a distinctive signature that sets them apart from the typical gravitational wave signals we've detected from black hole and neutron star mergers. We could be dealing with waveforms that have subtle, yet crucial, differences in their frequency or amplitude. This would require us to refine our models of gravitational wave propagation to account for these potential signals. Theoretical physicists are currently developing models to predict these unique signals. These models are based on different assumptions about the structure and properties of quasi-stable exotic compact objects, which may include the presence of an exotic matter core, a solid surface, or a non-singular interior. If we detect gravitational waves or electromagnetic signals that don't quite match the expected patterns for known objects, it could be a sign that we are encountering one of these exotic compact objects. At the forefront of this search is the international network of gravitational wave detectors, such as LIGO, Virgo, and CAGRA. These detectors have already given us remarkable insights into the dynamics of black holes and neutron stars. In the future, as these detectors become more sensitive, they could potentially detect the faint signals from quasi-stable exotic compact objects, providing us with the first definitive evidence of their existence. In parallel, the study of high-energy astrophysics could also provide important clues. Instruments like the Event Horizon Telescope, which captured the first-ever image of a black hole, or the upcoming James Webb Space Telescope, which will provide unprecedented views of distant galaxies, could help identify potential candidates for these exotic objects. The ability to observe objects at different wavelengths of light will allow us to search for subtle signatures that could hint at the presence of an exotic compact object. The role of quantum mechanics in these objects is also an exciting area of exploration. The idea that gravity and quantum forces can work together to produce a stable object like a gravistar or a boson star is revolutionary. Understanding how quantum fields might contribute to the stability of these objects could shed light on the long-standing problem of quantum gravity. For years, physicists have been trying to reconcile the principles of quantum mechanics with the theory of general relativity, and quasi-stable exotic compact objects could hold the key to solving this puzzle. If these objects truly exist, they would offer a unique opportunity to study the nature of quantum spacetime. For example, some of these exotic objects could involve the formation of quantum fields at extremely high densities, potentially leading to the creation of new exotic particles. By studying how these objects interact with light and matter, we might be able to test the predictions of quantum gravity theories in a way that was previously impossible. In the broader context of cosmology, the discovery of quasi-stable exotic compact objects would provide new insights into the evolution of the universe. Understanding how these objects form and evolve could give us clues about the early universe, especially in the moments following the Big Bang. These objects might be relics of an earlier cosmic era, providing us with a window into the universe's formative stages. Furthermore, if these objects are more common than we currently think, they could play a significant role in the formation and structure of galaxies, stars, and other cosmic phenomena. Ultimately, the discovery of quasi-stable exotic compact objects would not just be a triumph for theoretical physics. It would mark a new chapter in our understanding of the universe. These objects represent a bridge between the known and the unknown, a key that could unlock some of the deepest mysteries of the cosmos. As we continue to push the boundaries of observation and theory, we may one day look back and realize that these strange objects were the missing pieces of the cosmic puzzle we have been trying to solve for centuries. As we continue to explore the universe in search of quasi-stable exotic compact objects, it is essential to consider the broader implications of their potential existence. These objects could change not just our understanding of astrophysics, but also our perspective on the very nature of space and time. The idea that there are objects that sit between the familiar categories of black holes and neutron stars is both perplexing and fascinating. If they exist, they represent a completely new class of cosmic phenomena, one that could redefine what we thought we knew about gravitational physics, quantum mechanics, and the fabric of the universe itself. To truly appreciate the potential significance of these objects, we must delve deeper into the concept of stability. Stability in the context of astrophysical objects is typically understood as the ability to resist collapse under extreme pressure or gravity. Black holes, for instance, are considered stable in the sense that once they form, they persist indefinitely, at least until they are consumed by another massive object or evaporate via Hawking radiation. Neutron stars, while incredibly dense and subject to immense gravitational forces, are stable in their own right, maintained by the degeneracy pressure of neutrons. But quasi-stable exotic compact objects are thought to exist in a delicate balance. They are stable, but not in the same way as black holes or neutron stars. Their stability could be attributed to the presence of exotic matter or other novel mechanisms that we are only beginning to understand. Exotic matter is typically defined as matter that possesses unusual properties, such as negative mass or strange interactions with gravity. The precise role of exotic matter in maintaining the stability of these objects remains an open question, and it may ultimately require new physical theories to fully explain. The key to their stability might lie in the unique interactions between gravity and the quantum fields that permeate space-time. In traditional models, gravity is a classical force, described by general relativity, while quantum mechanics governs the behavior of particles on the smallest scales. However, in the case of quasi-stable exotic compact objects, these two realms may not remain separate. The gravitational field around these objects could be influenced by quantum fluctuations in a way that prevents the formation of a singularity, leading to the formation of a stable, yet exotic, compact object. This potential fusion of quantum and gravitational physics has profound implications for our understanding of the universe. For years, physicists have been searching for a theory of quantum gravity, a unified framework that can describe both the very large and the very small. Quasi-stable exotic compact objects could offer a glimpse into this unknown realm, where the rules of general relativity and quantum mechanics are no longer distinct. By studying the properties and behavior of these objects, we could learn how these two theories might be reconciled in a single, cohesive framework. In addition to their theoretical significance, quasi-stable exotic compact objects could also play a critical role in understanding the evolution of galaxies and the distribution of matter in the universe. While we often associate black holes with the centers of galaxies, especially supermassive black holes, quasi-stable exotic compact objects could also be present in these regions, potentially influencing the dynamics of star formation and galaxy evolution. If they are common in the universe, they could provide a new perspective on how galaxies are structured and how they evolve over time. One of the most intriguing aspects of these objects is the possibility that they could be responsible for some of the unexplained phenomena we observe in the universe. For instance, certain high-energy cosmic events, such as gamma-ray bursts or fast radio bursts, might be explained by the interactions of matter and energy around quasi-stable exotic compact objects. These objects might have unique electromagnetic signatures, possibly emitting radiation in ways that black holes and neutron stars cannot. If we can identify these signatures, it could open up an entirely new branch of astrophysics focused on the study of these objects and their role in cosmic events. Another area where quasi-stable exotic compact objects might have a significant impact is in the study of gravitational wave astronomy. As mentioned earlier, the merger of two black holes or two neutron stars produces detectable gravitational waves. However, the merger of two quasi-stable exotic compact objects might produce a distinct gravitational wave signal, one that could be different in frequency, amplitude, or duration. Detecting such waves could provide invaluable insights into the properties of these objects and help us confirm their existence. Gravitational wave detectors, such as LIGO and Virgo, have already revolutionized our understanding of the universe by allowing us to listen to the vibrations of space-time caused by distant cosmic events. As these detectors become more sensitive and more advanced, they will be able to pick up on the faintest signals, potentially identifying the signature of quasi-stable exotic compact object mergers. These observations would not only provide evidence for the existence of these objects, but also offer a new way to study the properties of the extreme environments in which they exist. Looking to the future, the development of next-generation space telescopes and observatories could provide us with new tools to explore these objects in greater detail. For example, the James Webb Space Telescope, set to launch in the coming years, will be capable of observing distant galaxies and stellar remnants in unprecedented detail. With its ability to capture infrared light, it could uncover the presence of exotic compact objects in places where optical telescopes have failed to see. Additionally, the upcoming LISA, Laser Interferometer Space Antenna, mission, which aims to detect low-frequency gravitational waves, could offer a new avenue for studying these objects through their gravitational wave emissions. All of this points to an exciting future in astrophysics, where the discovery and study of quasi-stable exotic compact objects could revolutionize our understanding of the universe. These objects, which sit on the edge of known physics, may hold the answers to some of the most profound questions in science. What is the true nature of gravity? How do quantum and classical forces interact in extreme environments? What is the fate of matter and energy in the most extreme conditions the universe has to offer? The answers to these questions could come from the study of quasi-stable exotic compact objects, objects that challenge our assumptions and push the limits of our understanding. The search for these objects will continue to inspire astronomers, physicists, and cosmologists for years to come. As technology advances and our understanding of the universe deepens, we may soon uncover the secrets of these enigmatic objects. Their discovery could be one of the most significant milestones in the history of science, providing new insights into the fundamental workings of the cosmos. In the meantime, we are left to wonder, could these objects be lurking in the vast reaches of space, waiting to be discovered? And if they are, what secrets do they hold about the nature of the universe, the laws of physics, and the origins of everything we know? The journey toward uncovering the secrets of quasi-stable exotic compact objects will require more than just theoretical predictions and computational simulations. It will require a concerted effort from astronomers, physicists, and engineers working together across various disciplines. The potential for groundbreaking discoveries is immense, but it is crucial to acknowledge that finding direct evidence of these objects will be a monumental challenge. The vast distances of space, the faint signatures they might leave, and the complexity of their behavior present significant obstacles. However, these challenges only make the pursuit more exciting, as each breakthrough brings us closer to answers that could fundamentally alter our understanding of the universe. To make this search a reality, we need more advanced tools and techniques. One of the key aspects of studying any astrophysical phenomenon is observing its interactions with light and other forms of electromagnetic radiation. For quasi-stable exotic compact objects, this task is particularly difficult. Their potential to avoid the singularities and event horizons typical of black holes means that they might not emit radiation in the same way we expect from these more familiar objects. Instead, they could produce unique electromagnetic signatures that could be very subtle, requiring highly sensitive instruments to detect them. This is where next-generation telescopes come into play. Space-based observatories such as the James Webb Space Telescope, JWST, will allow astronomers to observe distant galaxies and cosmic phenomena in unprecedented detail. The infrared capabilities of JWST will provide an entirely new perspective on the universe, allowing us to detect the faintest light from exotic objects that might otherwise be invisible to current instruments. By focusing on the infrared spectrum, we may be able to identify the thermal emissions or other signals that could hint at the presence of quasi-stable exotic compact objects. These observations could provide the crucial first step in confirming their existence, leading to new methods for studying these objects from a distance. Additionally, the advent of gravitational wave astronomy is set to play a pivotal role in the study of quasi-stable exotic compact objects. The Laser Interferometer Gravitational Wave Observatory, LIGO, and the Virgo detector have already provided us with the first direct detections of gravitational waves, offering us a new way to hear the universe. The merger of black holes and neutron stars has already yielded important insights into the nature of these extreme objects. But as mentioned earlier, the merger of quasi-stable exotic compact objects might produce a distinct signal. These signals could be characterized by subtle differences in their waveform, frequency, and amplitude, giving us clues about the properties of the objects involved. As gravitational wave detectors become more advanced, with future projects such as the Laser Interferometer Space Antenna, LISA, offering even greater sensitivity, we may be able to detect these unique waveforms with much greater accuracy. LISA, which is set to launch in the 2030s, will be able to detect low-frequency gravitational waves, which are produced by events such as the mergers of supermassive black holes or potentially exotic compact objects. The data gathered from such observations could provide direct evidence for the existence of these elusive objects and give us a new tool to study them in detail. Yet, while these instruments provide us with incredible potential, the study of quasi-stable exotic compact objects also depends on the development of new theoretical models. Current astrophysical models of compact objects, based on general relativity and standard models of particle physics, often do not predict the existence of these exotic objects. As a result, scientists will need to develop new theories that can accommodate the peculiar properties of quasi-stable exotic compact objects. These models will need to bridge the gap between quantum mechanics and general relativity, providing a unified framework that can explain the behavior of matter and energy in extreme environments. Theoretical physicists have long sought a theory of quantum gravity, a framework that would seamlessly integrate quantum mechanics with the theory of general relativity. The existence of quasi-stable exotic compact objects could offer a valuable testing ground for such a theory. These objects, by their very nature, might expose the limitations of our current understanding of gravity and quantum fields. The quantum fluctuations near these objects could reveal how gravity behaves at extremely small scales, providing insight into the elusive nature of spacetime at the Planck scale. In this sense, the study of these objects could be a stepping stone toward a deeper understanding of the fundamental laws of the universe. But even beyond the quest for new theories, the discovery of quasi-stable exotic compact objects could have profound implications for the philosophy of science. Our current understanding of the universe is built upon centuries of scientific discovery, each breakthrough adding another layer to our understanding of the cosmos. The existence of these objects would represent a shift in that understanding, showing that there are still vast mysteries in the universe that remain beyond our grasp. The pursuit of knowledge, especially in a field as complex as astrophysics, often involves asking questions that challenge the very assumptions we hold about reality. Quasi-stable exotic compact objects are just such a question. They force us to reconsider our ideas about the nature of matter, gravity, and the universe itself. In the grand scheme of things, the search for quasi-stable exotic compact objects is part of a larger endeavor, the quest to understand the universe at the deepest level. Just as the discovery of black holes and neutron stars revolutionized our understanding of the cosmos, the identification and study of these enigmatic objects could unlock new realms of knowledge. The implications of such a discovery could extend far beyond the field of astrophysics, potentially influencing fields like cosmology, quantum mechanics, and even philosophy. The study of exotic objects could challenge our very conceptions of space, time, and the fundamental nature of reality. As we move forward in this pursuit, we will undoubtedly encounter many challenges. There will be setbacks and obstacles, as there always are when exploring the unknown. But with each challenge comes an opportunity for growth and discovery. The search for quasi-stable exotic compact objects will continue to push the boundaries of science, encouraging collaboration across disciplines, advancing our technology, and inspiring new ways of thinking about the universe. It is a journey that could ultimately lead to a deeper understanding of the cosmos and our place within it. And as we venture into the unknown, we may come to realize that the universe is far more mysterious and wondrous than we ever imagined. The question remains, are these quasi-stable exotic compact objects already out there, hidden in the vast reaches of space, waiting for us to find them? And if so, what secrets do they hold about the universe's deepest mysteries? As we look deeper into the vastness of space, we are constantly reminded of the mysteries that lie just beyond our current understanding. Quasi-stable exotic compact objects, with their peculiar characteristics, represent one of the final frontiers in our quest to unravel the cosmos. Their potential to exist in the dense, violent regions of the universe, like the centers of galaxies or in the remnants of stellar collisions, suggests that they could hold crucial information about the nature of matter, space-time, and even the origins of the universe itself. These objects may be the key to answering fundamental questions that have perplexed scientists for centuries, such as the true nature of gravity, the behavior of matter at extreme densities, and the limits of our current physical theories. In order to uncover these secrets, the scientific community must remain steadfast in its pursuit of new methods of observation and analysis. Just as the discovery of black holes and neutron stars required groundbreaking innovations in technology, the detection of quasi-stable exotic compact objects will likely depend on the development of entirely new approaches. These objects may not emit detectable electromagnetic radiation in the same way that traditional black holes do, and their interactions with surrounding matter may be more subtle. This makes them difficult to spot using conventional methods, but it also means that when we finally do detect them, it will be a moment of triumph, a moment that could redefine our understanding of the universe. One promising avenue for exploring quasi-stable exotic compact objects is through their potential interactions with dark matter. Dark matter, which constitutes a significant portion of the universe's total mass, has yet to be directly observed, but its gravitational effects are clearly evident. Some theorists propose that quasi-stable exotic compact objects could be connected to dark matter in some way. If these objects are indeed made up of exotic matter or some form of quantum material not yet discovered, they could be part of the dark sector of the universe. Investigating how these objects interact with dark matter could lead to groundbreaking discoveries in both cosmology and particle physics. This could help us better understand the dark universe that lies hidden from our current detection methods. Another intriguing possibility involves the study of cosmic inflation. The theory of cosmic inflation posits that the universe underwent a rapid expansion in the moments immediately following the Big Bang. This theory has helped explain the large-scale structure of the universe and the uniformity of the cosmic microwave background radiation. However, there are still unanswered questions regarding the specifics of this process and the nature of the energy that fueled it. Quasi-stable exotic compact objects, with their potential for bizarre quantum properties, could hold clues to these questions. If these objects are connected to the high-energy conditions that existed in the early universe, their study could offer insights into the fundamental forces that shaped the cosmos during its infancy. There is also the possibility that quasi-stable exotic compact objects could be part of a new class of astrophysical phenomena that we have not yet even imagined. Just as the discovery of neutron stars and black holes fundamentally altered our understanding of stellar evolution, the detection of these objects could force us to rethink how stars, galaxies, and the entire universe evolve over time. Perhaps they are the remnants of objects that were once more stable but underwent extreme transformations due to gravitational collapse. Or maybe they represent an entirely new type of object that challenges our traditional categorization of cosmic bodies. The idea that there are still entire classes of objects out there waiting to be discovered is both exhilarating and humbling, reminding us that there is still so much we do not know about the universe. The future of quasi-stable exotic compact objects lies in the hands of the next generation of scientists and researchers. As our observational technologies improve, our understanding of the universe will continue to expand, and with it, the potential for groundbreaking discoveries. The pursuit of these objects will require a combination of creative thinking, innovative technology, and collaboration across disciplines. It will be a journey that pushes the boundaries of our knowledge and challenges our deepest assumptions about the nature of reality itself. As we continue to push the limits of our scientific knowledge, we must also be prepared for the possibility that some questions may remain unanswered for the foreseeable future. The search for quasi-stable exotic compact objects may take many years, or even decades, to bear fruit. But the beauty of science is that it is an ever-evolving pursuit. With each discovery, we come closer to understanding the intricate and awe-inspiring workings of the cosmos. The mysteries of the universe, no matter how elusive, are not beyond our reach. As long as we continue to ask questions, explore new possibilities, and strive for a deeper understanding, we will eventually unlock the secrets that lie hidden in the fabric of space-time. One of the most profound implications of discovering quasi-stable exotic compact objects is the potential shift in our view of the cosmos. For centuries, we have regarded black holes and neutron stars as the most extreme objects in the universe. These objects have captivated the imagination of scientists and the public alike, serving as the ultimate test cases for our theories of gravity and quantum mechanics. Yet, the discovery of quasi-stable exotic compact objects would upend this paradigm. Instead of seeing black holes as the ultimate end state for collapsing stars, we might discover that there are objects that defy our expectations of what is possible in the universe. This realization would have far-reaching implications for how we understand the life cycle of stars, the formation of galaxies, and the fundamental forces that govern the universe. It could change our understanding of everything from the birth of the universe to the ultimate fate of the cosmos. If these exotic objects are shown to exist, it would not only challenge our models of stellar evolution but could also provide crucial insights into the fundamental nature of matter and energy. We would be forced to reconsider our entire framework for understanding the universe, much as we did when we first realized that the Earth was not the center of the universe, or when we discovered the true nature of black holes. At the same time, the discovery of quasi-stable exotic compact objects would open up new avenues of research in astrophysics and cosmology. If these objects are indeed connected to the mysterious dark matter or the early stages of the universe, it could help us better understand the forces that shaped the cosmos in its infancy. These objects could provide direct evidence of the early universe's conditions and offer a window into the mysteries of the Big Bang. They might also give us clues about the behavior of matter under extreme conditions, pushing the limits of what we know about the fundamental forces of nature. The search for quasi-stable exotic compact objects is more than just an academic pursuit. It is a quest to better understand our place in the universe and the forces that govern it. It is a journey that could redefine our understanding of the cosmos, offering new insights into the nature of space-time, gravity, and the fundamental building blocks of the universe. And though the road ahead may be long and filled with challenges, the potential rewards are nothing short of extraordinary. As we continue to search for these enigmatic objects, we move closer to answering some of the most profound questions ever asked. And in doing so, we may just uncover a new chapter in the story of the universe. As we delve deeper into the exploration of quasi-stable exotic compact objects, we begin to realize that they hold the potential to reshape our understanding of the universe in ways that we have only begun to imagine. These enigmatic objects, which are theorized to be made up of some form of exotic matter, occupy a strange middle ground between the known and the unknown. Their very existence challenges our most fundamental concepts of physics, including the nature of matter, space-time, and the forces that govern the cosmos. The quest to identify and study quasi-stable exotic compact objects will undoubtedly drive the next generation of astrophysicists and cosmologists to develop new theories and observational techniques. The very fact that these objects are, by definition, quasi-stable means that they may exist for incredibly long periods of time but could also be fleeting, vanishing or transforming under certain conditions. This makes them extremely difficult to detect using traditional methods, and it is likely that we will need to develop entirely new technologies to observe them. Just as radio waves and X-rays open new windows into the universe, the detection of quasi-stable exotic compact objects may require the invention of entirely new observational tools or even the reimagining of existing ones. One avenue that could prove fruitful in the search for these elusive objects is gravitational wave astronomy. Gravitational waves, first predicted by Albert Einstein a century ago and directly detected in 2015, have opened up an entirely new way of observing the universe. These ripples in spacetime are produced by the acceleration of massive objects, such as merging black holes or neutron stars. While gravitational waves have already provided invaluable insights into the most extreme phenomena in the universe, it is possible that quasi-stable exotic compact objects could also generate detectable gravitational waves. Their interactions with nearby matter could produce subtle distortions in spacetime that we could potentially measure. This method of observation, however, would require unprecedented sensitivity and precision. Gravitational wave detectors like LIGO and Virgo, which have already detected waves from black hole mergers, may need to be upgraded or completely re-engineered to detect the more subtle signals that quasi-stable exotic compact objects could produce. However, even with these advanced tools, the search for these objects will likely be a long and painstaking process. The possibility of discovering such objects, however, is tantalizing. If they exist, it would not only expand our knowledge of astrophysics, but also provide us with new tools to probe the most mysterious corners of the universe. Another potential way to detect quasi-stable exotic compact objects lies in the study of high-energy astrophysics. Many of these objects may be associated with high-energy phenomena, such as gamma-ray bursts or intense radiation fields. These types of events are some of the most energetic processes in the universe, and have long been the subject of intense study. It is conceivable that quasi-stable exotic compact objects could play a role in such high-energy phenomena, either by interacting with nearby matter or by generating their own radiation. By studying these radiation emissions, astronomers might be able to uncover the presence of these objects. Additionally, the idea that quasi-stable exotic compact objects could be related to dark matter or even dark energy adds an exciting layer of complexity to their study. Dark matter, which makes up roughly 27% of the universe's total mass, has never been directly detected, but its presence is inferred through its gravitational effects on galaxies and galaxy clusters. Some researchers hypothesize that these exotic compact objects could be a form of dark matter. If this theory holds, then finding these objects would provide a direct detection of dark matter, a long-sought goal in modern astrophysics. It could also provide the key to understanding dark energy, the mysterious force driving the accelerated expansion of the universe. This connection between quasi-stable exotic compact objects and dark matter or dark energy underscores just how fundamental these objects could be to our understanding of the universe. If they are linked to the fabric of space-time itself, or the mysterious forces that govern cosmic evolution, then studying them could be the key to unlocking some of the most profound mysteries of the universe. It could potentially lead to breakthroughs in our understanding of the very nature of reality itself, and open new doors for future research. However, it's important to acknowledge that these objects remain, for now, entirely theoretical. We have not yet observed any direct evidence of their existence, and their detection will likely require significant advances in both theory and technology. But this should not diminish the excitement surrounding their potential discovery. The search for quasi-stable exotic compact objects is not just an academic exercise. It is a journey that could reshape our understanding of the universe and our place within it. Every new discovery, no matter how small, brings us closer to answering the deepest questions of existence. As we look forward to the future of astrophysics, it is clear that the study of these exotic objects will play a central role in the next phase of cosmic exploration. In the same way that the discovery of black holes and neutron stars revolutionized our understanding of the universe, the detection of quasi-stable exotic compact objects could mark the dawn of a new era in astrophysical research. These objects could offer a glimpse into the very fabric of space-time, providing clues about the nature of the cosmos that were previously thought to be beyond our reach. Yet, we must also be prepared for the possibility that the universe holds even deeper mysteries than we can currently fathom. The search for quasi-stable exotic compact objects is but one piece of the puzzle, and it is possible that future discoveries will lead us down entirely new and unexpected paths. Just as the discovery of quantum mechanics revolutionized our understanding of the microscopic world, the study of these objects could lead to an even deeper understanding of the fundamental laws of nature. The universe, as vast and complex as it is, may be filled with phenomena that challenge our most basic assumptions about reality. In the coming decades, we are likely to witness some of the most profound breakthroughs in the history of science. The discovery of quasi-stable exotic compact objects could be one of those breakthroughs, and when it happens, it will undoubtedly be a moment of triumph for humanity. It will mark a new chapter in our understanding of the universe, one in which we begin to unlock the deepest secrets of the cosmos. And in doing so, we may not only expand our knowledge of the universe but also gain a greater understanding of the very nature of existence itself. The story of quasi-stable exotic compact objects is just beginning. Their discovery may be some years away, but the work being done today, by scientists, researchers, and astronomers, will lay the foundation for this next great leap forward in our understanding of the universe. The mysteries of space are vast, and though we have uncovered many of its secrets, there are still plenty left to explore. With every question answered, more arise. With every discovery, we get one step closer to understanding the true nature of the cosmos. The search for quasi-stable exotic compact objects is but one chapter in this never-ending story, and we can only imagine what wonders lie ahead. As we continue to explore the mysteries of quasi-stable exotic compact objects, it's essential to understand just how fundamental these entities could be to the broader framework of astrophysics and cosmology. Their potential to reshape our understanding of gravity, quantum mechanics, and even the very nature of space-time makes them an essential focus of contemporary scientific research. The fact that these objects, though still purely theoretical, might exist on the cusp of our observational capabilities suggests that we are on the edge of a scientific breakthrough that could rival the discoveries of black holes or dark matter. When considering their formation, it's important to highlight that quasi-stable exotic compact objects may be born from extreme environments in the universe. Just as neutron stars and black holes are the remnants of collapsed stars, these exotic objects could arise from conditions involving ultra-high densities and pressures that we rarely encounter on Earth. In particular, they might form in the wake of supernova explosions or during the final stages of stellar evolution when stars are collapsing under their own gravity. These objects could exist in the spaces between galaxies, within the dense cores of galactic clusters, or even within the mysterious dark matter halos that surround galaxies. The theoretical nature of quasi-stable exotic compact objects means that their exact characteristics remain the subject of much debate. Some models suggest that they could be composed of strange quark matter, an unusual phase of matter that exists under extreme pressure, where quarks, the fundamental building blocks of protons and neutrons, are no longer confined within particles. Others propose that these objects could be made from some form of dark matter that interacts weakly with normal matter but may still produce gravitational effects that are detectable. If any of these ideas prove true, then quasi-stable exotic compact objects could represent an entirely new class of cosmic entities, one that exists beyond the boundaries of our current understanding of particle physics and astrophysics. The presence of these objects might also give us insight into the mysteries of the early universe. In the first few moments following the Big Bang, conditions were so extreme that new forms of matter and energy may have existed. Exotic compact objects could hold the key to understanding this primordial period of the universe, as their properties might reflect the physics of the very early universe, before the forces of gravity, electromagnetism, and nuclear forces had settled into the stable relationships we observe today. As we look for ways to detect these objects, it's important to consider the nature of their interactions with the environment around them. Because they are potentially composed of exotic matter, their interactions with ordinary matter could be quite different from those of black holes or neutron stars. For example, their gravitational influence might be detectable through distortions in the light from nearby stars or galaxies. Alternatively, their existence might be inferred by the way they affect the motion of stars or gas clouds in their vicinity. The challenge here is that many of these exotic objects could be very faint and difficult to distinguish from other types of compact objects, such as black holes or neutron stars. This means that the search for them will likely require highly advanced observational techniques, possibly combining multi-wavelength astronomy with gravitational wave detection and other cutting-edge methods. Despite these challenges, the potential rewards of discovering quasi-stable exotic compact objects are enormous. If these objects are real, they could provide direct evidence of new forms of matter and energy that exist beyond the standard model of particle physics. They could also offer new insights into the properties of dark matter, which remains one of the most perplexing mysteries of the universe. Understanding how these objects fit into the larger cosmic picture could allow scientists to piece together a more complete narrative of the universe's evolution, from its fiery birth to the present day. Perhaps the most exciting aspect of studying these objects, however, is the possibility that they might offer answers to some of the most profound questions in physics. For example, could quasi-stable exotic compact objects be a key to understanding the unification of forces? Could they offer new clues about quantum gravity and the behavior of matter at the Planck scale? These questions, which have remained unanswered for centuries, may soon be within our reach, thanks to the study of these mysterious objects. To study these objects more effectively, we will need to rely not only on the development of advanced technology but also on a deeper understanding of the theoretical models that describe their behavior. This will likely require a combination of computational simulations and analytical work, as scientists attempt to predict the properties of these objects and the way they interact with the surrounding environment. In particular, numerical simulations of compact objects, including exotic compact objects, will be essential for predicting their observable signatures and guiding future observational campaigns. These simulations, which require immense computational power, are already being used to model everything from the collision of black holes to the behavior of strange quark matter in extreme conditions. As we approach the possibility of detecting quasi-stable exotic compact objects, it's also important to consider how their discovery would impact our broader understanding of the universe. Their detection could provide a new window into the fundamental workings of space-time, allowing us to probe areas of the cosmos that are currently beyond our reach. It could lead to breakthroughs in our understanding of gravity, quantum mechanics, and the very fabric of reality. Furthermore, discovering new forms of matter, especially if they are linked to dark matter, could revolutionize our understanding of the universe's composition and structure. The mysteries of the cosmos may no longer be so elusive, and we may soon be able to begin piecing together the hidden parts of the universe's vast puzzle. If quasi-stable exotic compact objects are real, they could also change the way we think about the future of space exploration. Their discovery might open new avenues for studying the extreme environments of the cosmos. For example, if these objects are found to be located in the cores of galaxies or in the regions between galaxies, they could offer new opportunities for investigating the large-scale structure of the universe. They might also provide important clues about the distribution of dark matter and the formation of galaxies. The possibility of using these objects to further explore the cosmos also raises the prospect of new types of space missions. Missions designed to study these objects could involve new telescopes, new space observatories, and even probes designed to measure the gravitational effects of these objects up close. Space agencies might begin to develop new technologies capable of detecting the subtle signs of exotic compact objects, such as gravitational waves or the bending of light due to their gravitational influence. Given the extreme conditions under which quasi-stable exotic compact objects are theorized to exist, it's also possible that they could serve as natural laboratories for studying the fundamental forces of physics. Just as black holes allow us to probe the behavior of matter and energy in the presence of intense gravity, these exotic objects might provide a new opportunity to test theories of quantum mechanics and general relativity in environments that cannot be recreated on Earth. Studying these objects could offer valuable insights into the behavior of matter at the extremes of temperature, pressure, and density. Ultimately, the discovery of quasi-stable exotic compact objects would be more than just a triumph of scientific curiosity. It could be the key to answering some of the deepest questions about the nature of the universe itself. It could unlock new insights into the origins of the cosmos, the nature of dark matter, and even the future evolution of the universe. The road to finding these objects is long and fraught with challenges, but the potential rewards make it one of the most exciting frontiers in modern science. As the search for quasi-stable exotic compact objects, kekos, intensifies, the implications of their discovery extend far beyond the realm of theoretical astrophysics. These objects could hold the key to unlocking new branches of physics, potentially revealing deep connections between quantum mechanics, gravity, and the fundamental forces that govern our universe. They are, in essence, the theoretical bridges between the known and the unknown, acting as potential conduits through which we can probe the most extreme aspects of the cosmos. One of the most intriguing possibilities surrounding kekos is their potential connection to the mysterious concept of dark matter. As of today, dark matter remains one of the most compelling unsolved mysteries in physics. It is believed to account for approximately 27% of the universe's mass energy content, yet it remains entirely invisible, detectable only through its gravitational effects on visible matter. This enigmatic form of matter does not interact with light, meaning that we cannot see it directly. Kekos, if they are indeed made of strange or exotic forms of matter, might help explain some of the puzzling aspects of dark matter. In particular, strange quark matter, one of the leading candidates for kekos, could potentially be linked to dark matter. Strange quark matter is a type of quark gluon plasma, in which quarks are free to move independently, as opposed to being confined within protons and neutrons. Under the extreme conditions found in the cores of massive stars or in the final stages of stellar collapse, quarks could potentially form into strange quark matter, a substance that is far denser and more stable than ordinary matter. This kind of exotic matter could help to explain some of the gravitational effects that we observe in the universe, such as the anomalous motion of galaxies or the bending of light around invisible masses. The idea that kekos might play a role in the distribution of dark matter in the universe opens up exciting new avenues of research. If we could find ways to detect these objects, either through gravitational wave signals or by observing their effects on nearby stars and galaxies, it would not only provide direct evidence for the existence of dark matter but also allow us to probe the properties of this elusive substance in ways that were previously unimaginable. Moreover, Kekos might provide insights into the behavior of matter at extremely high densities, conditions that are almost impossible to replicate in a laboratory on Earth. The matter inside a keko could be in an entirely new state, one that behaves according to the laws of quantum chromodynamics, QCD, under extreme pressure and temperature. In these environments, quarks and gluons could be moving in ways that we have never observed before, leading to a deeper understanding of the fundamental forces at play within the atomic nucleus. For example, one of the key questions that kekos could help answer is whether there are other forms of matter that are stable at extremely high densities. We know that neutron stars, which are the remnants of massive stars that have gone supernova, are made almost entirely of neutrons. These stars are incredibly dense, so much so that a single teaspoon of neutron star material would weigh about 1 billion tons on Earth. But what if there are even denser objects, ones that could be made up of strange quarks, or other exotic forms of matter that we have not yet discovered? Kekos could be the key to answering this question. In addition to advancing our understanding of matter and dark matter, the study of kekos also holds promise for new breakthroughs in the field of general relativity. These objects are thought to exhibit gravitational effects that are different from those of black holes or neutron stars. If they are stable but exotic in nature, their gravitational influence could be subtle, yet profound, providing a new way to test Einstein's theory of gravity under extreme conditions. The unique properties of kekos might offer a glimpse into the behavior of spacetime at the most fundamental level, potentially shedding light on the elusive nature of gravity itself. One fascinating aspect of kekos is their potential to challenge our understanding of the very structure of spacetime. According to general relativity, black holes are the ultimate expression of gravitational collapse, where a star's core collapses into a singularity, an infinitely small point where gravity is so intense that not even light can escape. However, if kekos do indeed exist, they could represent a new type of object where gravity is still incredibly strong, but spacetime is not destroyed in the same way as it is inside a black hole. This could lead to a new way of thinking about the fabric of the universe, where extreme conditions give rise to new phenomena that do not fit neatly into our current models. For example, the existence of kekos might indicate that there are other ways for matter to collapse into extremely dense objects without the formation of a singularity. This could open the door to new models of gravity that go beyond the traditional framework, perhaps even providing clues about the long-sought theory of quantum gravity, a unified description of all fundamental forces that would merge the principles of quantum mechanics and general relativity. Moreover, if kekos are shown to interact with ordinary matter in unique ways, they could lead to new insights into how the fundamental forces of nature operate under extreme conditions. Such interactions could provide experimental data that could guide the development of a more complete theory of the universe, one that accounts for the behavior of matter and energy at all scales, from the subatomic to the cosmological. As we look ahead to the possibility of detecting these objects, it's clear that the next generation of telescopes and space observatories will play a crucial role. For example, gravitational wave detectors like LIGO and Virgo have already revolutionized our understanding of black holes and neutron stars, allowing us to observe ripples in spacetime caused by their collisions. In the future, these instruments might also be used to detect the faint signals produced by kekos. Additionally, advanced optical and radio telescopes could help us identify the subtle signatures of these objects, perhaps through their gravitational lensing effects, or the way they influence the motion of nearby stars. Ultimately, the study of kekos is not just a scientific endeavor, it's a journey that could lead to some of the most profound discoveries in the history of physics. These objects could help us answer some of the most fundamental questions about the nature of matter, gravity, and the cosmos itself. As we continue to probe the mysteries of the universe, the potential discovery of quasi-stable exotic compact objects could be one of the most significant milestones in our quest to understand the true nature of reality. The prospect of discovering quasi-stable exotic compact objects, kekos, could radically transform our approach to astrophysics and fundamental physics. These objects are, at their core, unlike anything we have observed so far in the universe. While black holes, neutron stars, and white dwarfs are familiar to us from years of astronomical research, kekos present a unique challenge because they might exist in a state of matter that is not found in the objects we typically study. Theoretical predictions about their structure and properties push the boundaries of known physics, and if we can confirm their existence, it could force us to reevaluate some of our most entrenched theories. One of the most striking features of kekos is their potential stability in a state of matter that would otherwise be highly unstable in conventional astrophysical contexts. For example, neutron stars are incredibly dense objects formed from the collapse of massive stars, where neutrons are packed so tightly together that they form a solid structure. These stars are the remnants of stars that have exhausted their nuclear fuel, and while they can be stable under certain conditions, they eventually succumb to further gravitational collapse, either collapsing into a black hole or, in some rare cases, undergoing a different kind of transition. The discovery of kekos would suggest the possibility of an entirely new phase of matter that allows for even greater densities without such a collapse. At the heart of this puzzle lies the question of what kind of matter could form a quasi-stable exotic compact object. This is where the connection to strange quark matter becomes especially intriguing. Strange quark matter, as hypothesized, could be the building block of kekos. Strange quarks are a type of elementary particle that is more massive than the up and down quarks that make up normal matter, like protons and neutrons. Under extreme pressures and temperatures, such as those found in the cores of collapsing stars, these strange quarks could form a new state of matter that is more stable than the conventional nuclear matter and neutrons. This strange matter could potentially be stable in environments where normal matter would fail to be stable, such as the interior of neutron stars or in the aftermath of supernovae. It might even be stable outside these extreme conditions, in the form of objects that remain stable for much longer timescales, possibly as quasi-stable exotic compact objects. This would mean that these objects could survive for far longer than other exotic forms of matter, such as black holes, and could provide a long-lasting source of insight into the fundamental properties of matter under extreme conditions. The density of strange quark matter is expected to be higher than that of nuclear matter, and it is thought to possess unique properties that could influence the behavior of a keko. For example, one theory suggests that the matter inside a keko might not behave according to classical models of gravity but instead exhibit quantum effects that allow it to remain stable despite the tremendous pressures exerted upon it. These objects could possess a kind of quantum stabilization that keeps them from collapsing into a singularity or being destroyed by the forces acting on them. In this way, kekos could offer a glimpse into a new realm of physics that we have yet to fully understand. Another critical aspect of kekos is their potential gravitational signature. As objects that are predicted to be incredibly dense and compact, kekos would exert a significant gravitational influence on their surroundings. However, unlike black holes, kekos would not be expected to have event horizons, the regions of space beyond which nothing, not even light, can escape. Instead, they might exhibit a more subtle form of gravitational influence, allowing light and other forms of radiation to pass by without being completely absorbed. This would make them potentially detectable by advanced gravitational wave detectors or by observing the gravitational lensing effects they produce as they warp the fabric of spacetime around them. Gravitational lensing, the bending of light around a massive object, is one of the key methods through which astronomers can detect the presence of otherwise invisible objects. If kekos are able to produce noticeable lensing effects, we could observe them by studying the distortions in the light from distant stars and galaxies. This would be similar to how astronomers detect dark matter by studying the way it influences the motion of galaxies. Even though kekos might not be directly observable through traditional means, such as visible light or X-rays, their presence could be inferred through their gravitational effects. The possibility of kekos also raises interesting questions about the evolution of the universe itself. If these objects are stable over cosmic timescales, they could play a significant role in the long-term dynamics of the cosmos. For example, they might serve as a source of gravitational waves, emitting ripples in spacetime that could be detected by future generations of gravitational wave observatories. These waves could carry with them valuable information about the properties of kekos and the extreme environments in which they formed. They might also provide a clue to the origins of some of the most energetic events in the universe, such as supernovae or the mergers of compact objects like neutron stars or black holes. Kekos might also help answer some of the long-standing questions about the nature of the early universe. In particular, they could provide insight into the conditions that existed shortly after the Big Bang, when the universe was in its infancy and matter was much more dense and energetic than it is today. Understanding how matter behaved during this early period could shed light on the processes that led to the formation of galaxies, stars, and other cosmic structures. Kekos, if they exist, might be relics from this early era, providing a direct link between the primordial universe and the modern cosmos. The hunt for quasi-stable exotic compact objects is just beginning, but already, it is sparking a revolution in our understanding of the universe. Whether or not these objects are eventually discovered, the very idea that such exotic forms of matter might exist challenges everything we thought we knew about the behavior of matter under extreme conditions. As astronomers continue to refine their search for kekos, using next-generation telescopes, gravitational wave detectors, and other advanced instruments, we are likely to learn more about the nature of the universe than ever before. The existence of kekos would not just answer questions about dark matter or the behavior of matter in extreme environments. It would fundamentally change our understanding of the universe itself. These objects could reveal new aspects of the fundamental forces that govern everything from the smallest particles to the largest galaxies. They represent a frontier in physics that is only just beginning to be explored, and their discovery could be one of the most significant milestones in the history of science. As we continue to probe the mysteries of the cosmos, the search for quasi-stable exotic compact objects will undoubtedly remain one of the most exciting and important areas of research in the years to come. As we delve deeper into the potential of quasi-stable exotic compact objects, kekos, it becomes clear that their study could usher in a new era of astrophysical discovery. These objects may serve as a bridge between the known and the unknown, offering us glimpses into the very fabric of space-time and the fundamental nature of matter itself. With each new theory and model proposed, scientists inch closer to the moment when the first direct evidence of kekos might be observed, forever altering our perspective on the cosmos. One of the most captivating aspects of kekos is their connection to the concept of quantum gravity. Quantum gravity seeks to reconcile the two pillars of modern physics, general relativity, which describes the force of gravity on large scales, and quantum mechanics, which governs the behavior of particles on the smallest scales. These two theories have been incredibly successful in their respective domains but are fundamentally incompatible when applied to extreme environments, such as those found near black holes or in the interior of stars. The search for a theory of quantum gravity is one of the most profound challenges in theoretical physics. The discovery of kekos could provide the key to unlocking this mystery. Because these objects are predicted to be located in regions of space where quantum effects and gravitational forces interact in complex ways, they could provide the experimental data needed to test and refine theories of quantum gravity. In particular, the quantum properties of kekos might reveal new insights into the nature of spacetime itself, such as the existence of quantum foam or other exotic phenomena that have been hypothesized but never observed. Additionally, kekos could offer new perspectives on the behavior of matter under extreme conditions. The pressure and temperature at the core of a neutron star or a collapsing star are already extreme, but the matter inside kekos is thought to exist in an even more exotic state. The study of these objects could reveal new states of matter that have never been observed in laboratories on Earth, expanding our understanding of the possible forms that matter can take. This might include new forms of superconductivity, new types of exotic particles, or even entirely new phases of matter that we cannot yet imagine. The formation of kekos could also provide valuable information about the life cycle of massive stars. Currently, when massive stars exhaust their nuclear fuel, they can collapse into black holes or neutron stars, depending on their mass. But the process by which kekos might form could be entirely different, potentially offering a glimpse into an alternative end state for massive stars. This could revolutionize our understanding of stellar evolution and the final stages of massive star systems, and help us learn more about the processes that lead to the formation of the most extreme objects in the universe. Moreover, kekos could potentially be related to the enigmatic phenomenon of dark energy. Dark energy is thought to be responsible for the accelerated expansion of the universe, yet it remains one of the greatest unsolved mysteries in cosmology. If kekos are indeed a new phase of matter, they could provide valuable clues about the fundamental nature of dark energy and its role in the evolution of the universe. This connection could reveal hidden relationships between matter, energy, and space-time that are currently beyond our reach. As we explore the possibility of kekos, we must also consider the technological advancements that will be required to detect them. Currently, our most advanced methods for detecting compact objects, such as gravitational wave observatories and advanced telescopes, may not be enough to observe kekos directly. These objects might be too small or too subtle in their gravitational effects to be easily spotted with current instruments. However, as our technology continues to improve, the likelihood of detecting kekos increases. For example, the next generation of gravitational wave detectors, like the Laser Interferometer Space Antenna, LISA, could be sensitive enough to detect the subtle gravitational waves produced by these objects, providing us with direct evidence of their existence. Similarly, advancements in observational astronomy may help us spot kekos through other means, such as through their electromagnetic emissions or the gravitational lensing they might cause. While kekos are not expected to produce the same kind of intense radiation as black holes or neutron stars, their influence on nearby matter might lead to observable phenomena that we can detect with future telescopes. Observations of the cosmic microwave background, the afterglow of the Big Bang, could also provide indirect evidence of kekos, especially if they played a significant role in the early universe. In the meantime, the theoretical work on kekos continues to evolve. Physicists and astrophysicists are constantly refining their models, trying to predict the specific properties and behaviors of these objects. For example, one area of active research is the equation of state, EOS, for the matter inside kekos. The EOS describes how matter behaves under extreme conditions of pressure and temperature, and understanding it is crucial for predicting the stability of kekos. By developing a more accurate EOS, scientists hope to better understand how kekos could form, what their interior might look like, and how they might interact with their environment. Another avenue of research involves the study of the fundamental forces that might be at play inside kekos. While gravity is the dominant force in many astrophysical contexts, the interactions between particles at the quantum level could be just as important in determining the properties of kekos. Understanding the role of the strong and weak nuclear forces, as well as the electromagnetic force, could help us develop a more complete picture of the internal structure of these objects. As the search for kekos continues, it is important to remember that even if these objects are not discovered in the immediate future, the theories and models being developed to explain their existence will have far-reaching implications for our understanding of the universe. Whether or not kekos exist, the effort to understand them is pushing the boundaries of physics, challenging our assumptions about the nature of matter, space, and time. Ultimately, the pursuit of knowledge about quasi-stable exotic compact objects is more than just an academic exercise. It is an essential part of the broader quest to understand the universe in all its complexity. Whether we find kekos or not, the journey to uncover their secrets will undoubtedly lead to new discoveries, new theories, and a deeper appreciation of the mysteries that still await us in the cosmos. The existence of kekos could change everything, not just for astrophysics but for the very foundations of science itself. The search for these strange and elusive objects is only just beginning, and the next few decades could hold some of the most exciting breakthroughs in the history of science. As the search for quasi-stable exotic compact objects, kekos, continues to advance, we are slowly beginning to shift our understanding of the very nature of space-time, matter, and the fundamental forces that shape the universe. The study of kekos could open the door to a host of scientific revolutions, as it challenges the boundaries of what we thought was possible in the cosmos. From new theories about quantum gravity to the identification of unknown states of matter, the potential discoveries awaiting us are vast and varied. One of the areas where kekos could have profound implications is in our understanding of singularities. Singularities, the regions of space where gravity becomes infinite, have been the subject of intense theoretical study. Black holes, the most well-known of these objects, are thought to contain singularities at their cores. However, the nature of these singularities has long remained a mystery. Many physicists believe that a theory of quantum gravity, which would unify general relativity and quantum mechanics, is required to fully understand what happens inside a black hole and whether singularities can truly exist. Kekos, by their very nature, offer a unique opportunity to test our ideas about singularities. If these objects can exist in a stable state without collapsing into a true singularity, it would imply that the singularity concept might need to be re-examined. Instead of a point of infinite density, the collapse of matter could lead to a more complex state, one that retains certain quantum properties while still exhibiting strong gravitational effects. This could help resolve some of the paradoxes and inconsistencies that arise when we try to apply both quantum mechanics and general relativity to extreme environments. Moreover, the search for kekos may help us answer one of the biggest questions in astrophysics: the true nature of dark matter. Dark matter, the mysterious substance that is believed to make up a large portion of the universe's mass, has been the subject of extensive research, yet it remains largely elusive. Some theories propose that dark matter could be composed of exotic compact objects, potentially even kekos themselves. If this is the case, the discovery of kekos could have major implications for our understanding of the structure and evolution of the universe. The relationship between kekos and dark matter could be incredibly complex. For example, some models suggest that dark matter could consist of particles that interact weakly with ordinary matter, making them difficult to detect. However, kekos, by virtue of their exotic and compact nature, might offer a new way to detect dark matter. If kekos do indeed exist, they might leave behind observable signatures that could help us identify the elusive dark matter particles. This would be a major breakthrough, as it could provide direct evidence for the existence of dark matter and help solve one of the most enduring mysteries in modern science. The study of kekos also has the potential to enhance our understanding of gravitational waves. These ripples in space-time, predicted by Einstein's general theory of relativity, were first directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. Since then, gravitational wave astronomy has opened up a new window on the universe, allowing us to observe cosmic events that were previously invisible to traditional telescopes. Gravitational waves produced by merging black holes, neutron stars, and other compact objects have already provided valuable insights into the nature of space-time and the behavior of matter in extreme conditions. Kekos could produce gravitational waves that are distinct from those of other objects. For instance, their unique internal structure might cause them to oscillate or vibrate in ways that produce characteristic gravitational wave signals. These signals could provide us with valuable information about the composition and properties of kekos, as well as the environments in which they form. If kekos are related to dark matter or other exotic forms of matter, their gravitational wave signatures could reveal new insights into the fundamental nature of the universe. As we consider the possibility of kekos, it is also important to acknowledge the limitations of our current observational tools. While advancements in gravitational wave detection and high-resolution telescopes have already allowed us to make groundbreaking discoveries, kekos might still remain elusive for some time. These objects may be too small, too distant, or too faint to detect with our current instruments. However, this should not discourage us. In fact, the very challenges posed by kekos may inspire new technological innovations and observational techniques that will push the boundaries of science even further. One of the most promising areas of technological development in the quest to detect kekos is the advancement of interferometry. Interferometers, like the ones used in LIGO and the upcoming LISA mission, rely on the precise measurement of the interference between light waves to detect tiny changes in space-time. As technology improves, these instruments will become more sensitive, allowing us to detect even the faintest gravitational waves from kekos. The next generation of interferometers, such as the planned space-based LISA mission, could open up entirely new avenues for studying kekos and other exotic objects in the universe. Another exciting possibility is the use of electromagnetic observations to detect kekos. While kekos themselves may not emit the same intense radiation as black holes or neutron stars, they could still influence their surroundings in detectable ways. For example, They might cause nearby matter to behave in unusual ways, leading to observable radiation signatures. Additionally, kekos could affect the path of light passing near them, producing gravitational lensing effects that could be detected by future telescopes. By combining gravitational wave and electromagnetic observations, we could obtain a more complete picture of these enigmatic objects. The study of kekos could also help us refine our understanding of the early universe. In the moments following the Big Bang, the universe was in a highly energetic and dense state, with particles and radiation interacting in complex ways. Some theories suggest that objects like kekos could have formed during this early period, perhaps as a result of quantum fluctuations or other exotic processes. If kekos were present in the early universe, they could have played a crucial role in the formation of the cosmic structure that we observe today. Understanding how these objects might have shaped the early universe could provide us with valuable clues about the origins of galaxies, stars, and the fundamental forces that govern the cosmos. It is worth considering the broader implications of the discovery of kekos. If these objects do exist, they could fundamentally alter our understanding of the universe. From the way we think about black holes and dark matter to our ideas about quantum gravity and the fabric of space-time, kekos could open up entirely new realms of scientific inquiry. The discovery of kekos would be a monumental achievement, not only for astrophysics but for our collective understanding of the nature of reality itself. The search for quasi-stable exotic compact objects is one of the most exciting frontiers in modern astrophysics. These objects, which exist on the edge of what is currently known, could hold the key to unlocking many of the most profound mysteries of the universe. Whether they are the key to understanding dark matter, the resolution of quantum gravity, or the final stages of stellar evolution, kekos offer an unprecedented opportunity to expand our knowledge of the cosmos. The pursuit of these objects, driven by curiosity and the thirst for knowledge, promises to reshape our understanding of space, time, and the very fabric of reality. The road ahead is filled with challenges, but the potential rewards are greater than we can currently imagine. The implications of discovering quasi-stable exotic compact objects, kekos, stretch far beyond the boundaries of current astrophysical models. If we were to confirm their existence, kekos could lead to paradigm shifts in multiple fields of study, from gravitational physics to cosmology. These objects could hold the key to understanding phenomena that have long eluded scientists, such as the exact nature of dark energy, the behavior of matter in extreme environments, and even the unification of the fundamental forces of nature. To begin, the detection of kekos could serve as a window into the realm of quantum gravity, a theory that has been sought after for decades but remains elusive. Quantum gravity aims to unify the principles of general relativity, which governs the macroscopic world of gravity, and quantum mechanics, which rules the microscopic domain of subatomic particles. The extreme conditions surrounding kekos, including their immense density and gravitational forces, would likely require a quantum treatment of gravity to fully comprehend their behavior. In this sense, kekos could be a crucial testing ground for theories of quantum gravity. One of the most significant challenges in reconciling general relativity and quantum mechanics is the issue of singularities. Singularities are thought to exist at the centers of black holes, where gravitational forces are so intense that they cause a breakdown in the laws of physics. According to classical general relativity, these singularities represent points of infinite density. However, quantum mechanics suggests that such infinities cannot exist, as quantum effects should prevent matter from collapsing into a singularity. If kekos exist as a stable alternative to black holes, they could potentially offer insights into how gravity behaves at extreme scales and provide a solution to the singularity problem. Furthermore, kekos could play a crucial role in resolving the mysteries surrounding dark energy, the force believed to be responsible for the accelerated expansion of the universe. Dark energy is a pervasive and mysterious substance that makes up about 70% of the universe's energy density, yet its nature remains unknown. Some theories suggest that kekos could be related to dark energy, perhaps as a manifestation of exotic matter that has unusual gravitational properties. By studying the behavior of kekos, particularly their interaction with light and matter, scientists could gather valuable data that sheds light on the true nature of dark energy. In addition to their potential role in understanding dark energy, kekos could provide crucial information about the formation and evolution of galaxies. The process of galaxy formation involves the collapse of large clouds of gas and dust under the influence of gravity, leading to the creation of stars and other celestial objects. Kekos could offer new insights into the early stages of galaxy formation, particularly in terms of how matter behaves in the presence of strong gravitational fields. These objects could also provide a way to test theories of cosmic inflation, the rapid expansion of the universe in the first moments after the Big Bang. Another area where kekos could have a profound impact is in the study of astrophysical jets. Jets are high-energy streams of particles that are often observed emanating from the poles of black holes and neutron stars. These jets are thought to be driven by intense magnetic fields and the accretion of matter onto the central object. Kekos, with their unique properties and internal structures, could potentially produce jets that differ from those produced by black holes or neutron stars. By studying these jets, scientists could gain a deeper understanding of the mechanisms that drive them and the role that kekos play in these processes. The search for kekos could also lead to advancements in observational technology. As we attempt to detect these exotic objects, we will be forced to develop new instruments and techniques that can observe the universe with unprecedented precision. One promising area of research is in the development of advanced interferometric arrays. These arrays, which use multiple telescopes working in concert to observe distant objects, could be instrumental in detecting the faint signals emitted by kekos. Additionally, the rise of gravitational wave astronomy offers another avenue for detecting kekos, as these objects could produce unique gravitational wave signatures that are distinct from those produced by black holes and neutron stars. The study of kekos could also help us refine our understanding of the cosmic web, the vast network of galaxies, clusters, and dark matter that make up the large-scale structure of the universe. Kekos, if they are related to dark matter or other forms of exotic matter, could provide new clues about the role of these mysterious substances in the formation of large-scale structures. Understanding how kekos interact with their surroundings could help us develop a more comprehensive picture of the evolution of the cosmos, from the Big Bang to the present day. As the search for kekos progresses, we may find that they are not only exotic curiosities but also central players in the ongoing story of the universe. The discoveries that lie ahead may not only redefine our understanding of astrophysics, but also transform the way we think about space, time, and the fundamental forces of nature. These objects, which exist on the cutting edge of scientific knowledge, offer a glimpse into the unknown, challenging our assumptions and pushing the limits of our understanding. One of the most exciting aspects of the potential discovery of kekos is the way it could inspire future generations of scientists. The quest to understand these objects is not just about answering specific questions, it is about expanding the boundaries of human knowledge and pushing the frontiers of exploration. Just as the discovery of black holes, neutron stars, and gravitational waves has revolutionized our understanding of the cosmos, the study of kekos has the potential to unlock entirely new realms of scientific inquiry. In this sense, kekos represent not just a scientific mystery, but a symbol of the curiosity and determination that drives human exploration. As we strive to unravel the secrets of these exotic objects, we are reminded of the boundless potential of scientific discovery and the incredible capacity of the human mind to explore the unknown. It is clear that we are only at the beginning of what could be an extraordinary journey. The mysteries that surround these objects are vast, and the challenges involved in studying them are immense. However, the rewards of uncovering their secrets are equally great. Whether kekos are real or remain theoretical, the search for these objects will undoubtedly lead to breakthroughs that extend far beyond the confines of astrophysics. The study of kekos has the potential to redefine our understanding of the universe and to open up new frontiers of discovery that we can only begin to imagine. With every new piece of evidence, we move closer to uncovering the deepest mysteries of the cosmos, and in doing so, we take another step toward understanding the very nature of reality itself. The journey into the study of quasi-stable exotic compact objects, kekos, is a path that leads into uncharted territory, exploring the very foundations of how we understand the universe. By their very nature, kekos challenge everything we think we know about compact astrophysical objects, pushing the boundaries of physics into new realms. While much of the theoretical framework surrounding kekos remains speculative, the implications of their possible discovery would extend far beyond any single field of science. These objects, if found to exist, could have profound consequences not only for astrophysics but for our entire understanding of space, time, and the fundamental forces that shape the universe. One of the most captivating possibilities posed by kekos is the nature of their internal structure. In contrast to conventional stellar remnants such as black holes and neutron stars, kekos may not possess a singularity or an event horizon. This would make them radically different from black holes, which are traditionally defined by the presence of an event horizon, an invisible boundary beyond which nothing, not even light, can escape. Instead, kekos may exhibit an intricate balance of forces that prevent gravitational collapse from reaching the point of singularity, creating a stable, albeit highly dense, structure. This opens up a host of questions about the kinds of matter and energy that could exist within these objects and how they could be sustained over time. There is also the intriguing possibility that kekos could provide insight into the elusive nature of dark matter. Dark matter, which makes up approximately 27% of the universe's mass-energy content, is invisible and interacts with normal matter only through gravity. Despite its importance, scientists have yet to directly detect dark matter particles, and its exact properties remain a mystery. Kekos, with their strange and exotic properties, could potentially provide a link to dark matter. Some theories suggest that kekos might be composed of exotic forms of matter, such as dark matter itself or other yet undiscovered particles. If kekos were found to be related to dark matter, they could revolutionize our understanding of this mysterious substance, offering a direct way to study its properties and behavior. Furthermore, kekos could shed light on the nature of quantum mechanics and general relativity. These two pillars of modern physics have been remarkably successful in their respective domains, but they are fundamentally incompatible when it comes to understanding extreme conditions like those found near black holes or within the early universe. Kekos, with their extreme densities and gravitational fields, could serve as a natural laboratory for testing theories of quantum gravity, a unified theory that attempts to reconcile the two. The behavior of matter in the vicinity of kekos could reveal new insights into the quantum structure of spacetime, providing vital clues about how the fabric of the universe behaves at the most fundamental level. Another fascinating aspect of kekos is their potential role in the evolution of the universe itself. Some cosmologists speculate that objects like kekos could play a role in the formation of large-scale structures in the cosmos, such as galaxies and galaxy clusters. If kekos are composed of exotic forms of matter, they could interact with regular matter in ways that influence the growth and distribution of cosmic structures. Their existence could have important implications for our understanding of how galaxies form, how they evolve, and how they interact with one another on cosmic scales. Additionally, kekos could offer a new way to probe the very early universe, helping to test models of cosmic inflation, the rapid expansion of the universe in its first moments. The detection of kekos could also open up new avenues for studying the dynamics of spacetime itself. General relativity predicts that extremely massive objects, such as black holes and neutron stars, warp spacetime in such a way that the curvature of space and time becomes extreme. Kekos, with their unusual properties, could provide a new type of spacetime distortion, one that might behave differently from the classical models of black holes and neutron stars. By studying how kekos warp spacetime, scientists could gain new insights into the nature of gravity and the structure of spacetime, particularly in environments where traditional models break down. This could have profound implications for the way we think about the fabric of the universe, and could lead to a deeper understanding of how gravity works at the most extreme scales. One of the most compelling reasons to search for kekos is the potential they hold for revealing the deep connection between quantum mechanics and gravity. For centuries, physicists have struggled to reconcile these two theories, each of which describes different aspects of reality. While general relativity provides an elegant description of the large-scale structure of the universe, quantum mechanics governs the behavior of the smallest particles. Yet when it comes to extreme environments, such as those near black holes, where both gravitational and quantum effects are significant, these two theories seem to be at odds with each other. Kekos could provide the key to understanding how these two frameworks can be unified, offering a unique opportunity to probe the deepest questions of theoretical physics. In addition to their role in theoretical physics, kekos could have significant practical applications as well. For example, the study of kekos could help refine our methods for detecting gravitational waves, ripples in spacetime caused by the acceleration of massive objects. Gravitational waves are a relatively new area of research, with the first direct detection occurring only in 2015. However, future detections of kekos could provide more precise measurements of these waves, helping to improve our understanding of the sources of gravitational waves and the behavior of spacetime. Additionally, the study of kekos could help improve our models of how matter behaves under extreme conditions, leading to advancements in fields such as high-energy physics and nuclear fusion. The search for kekos is still in its early stages, and there are many challenges ahead. Current observational technologies are not yet capable of directly detecting these objects, and much more research is needed to understand their potential properties and behavior. However, as technology continues to advance, it is likely that we will develop new tools that will allow us to probe the universe in ways that were once thought impossible. Instruments like the Event Horizon Telescope, which has already provided stunning images of black holes, and future space-based observatories may be key in the search for kekos. Moreover, the detection of kekos would not only be a triumph of scientific achievement, but also a profound moment in human history. The discovery of these objects would mark a turning point in our understanding of the universe, providing a new window into the most extreme environments in space. It would be a reminder of the infinite mysteries that still lie beyond our reach, waiting to be uncovered. And it would inspire future generations of scientists and explorers to continue pushing the boundaries of knowledge, seeking to answer the most fundamental questions about the nature of reality itself. The existence of kekos, whether confirmed or not, serves as a testament to the power of human curiosity and the relentless pursuit of knowledge. In many ways, the search for these objects embodies the spirit of scientific exploration, uncovering the unknown, questioning established theories, and daring to dream of a deeper understanding of the universe. Whether they exist in the distant corners of space or remain a theoretical concept, kekos are a reminder that the universe is far more mysterious and complex than we can ever fully comprehend. The more we explore the theoretical landscape of quasi-stable exotic compact objects, kekos, the more we realize that they represent a profound challenge to our understanding of the cosmos. If these objects exist in the manner described by theoretical physicists, they could serve as key players in some of the universe's most fundamental mysteries. But the questions raised by their potential existence go far beyond astrophysical observations. They delve deep into the very fabric of spacetime, quantum mechanics, and the nature of matter itself. One of the most compelling aspects of kekos is their potential to offer insights into the behavior of matter at extremes. Traditional compact objects, such as white dwarfs, neutron stars, and black holes, are well understood in certain contexts. White dwarfs and neutron stars represent the endpoints of stellar evolution, with their matter in an ultra-dense state due to gravitational collapse. Black holes, meanwhile, are thought to form when matter collapses beyond the point of no return, creating an event horizon where classical physics breaks down. However, kekos could provide us with a new class of objects that might lie somewhere between these known end states, presenting an entirely new way of thinking about the collapse of matter. Theoretical models predict that these objects could be the result of exotic processes, possibly involving quantum gravity or other unknown forces that act in unusual ways. The idea of a quasi-stable object suggests that it doesn't collapse into a singularity, as a black hole would, but rather exists in a delicate equilibrium. Such an object could be incredibly dense and compact, perhaps even more so than a neutron star, but without the defining features of a black hole, like the event horizon. This kind of object would challenge our understanding of gravitational collapse and could reveal new phenomena in high-energy astrophysics. One avenue of research focuses on how kekos might form. Some hypotheses suggest that these objects could emerge from the collapse of a star or some other massive body that doesn't follow the typical patterns observed in stellar evolution. Instead of forming a black hole, the gravitational collapse might stabilize at a certain density, resulting in a dense, yet stable object. Alternatively, it's possible that kekos could arise from the behavior of extremely high-energy particles or fields, which could interact in ways that produce stable, exotic forms of matter that we have yet to fully understand. The exact processes behind their formation remain speculative, but they could be tied to phenomena that have never been observed in nature. If kekos are indeed real, their discovery could revolutionize our approach to studying the universe. For one, they might allow us to observe new forms of matter that behaves in ways that are unlike anything we have encountered before. This could help to explain some of the unanswered questions about the nature of exotic matter, such as dark matter and dark energy, both of which are believed to make up the vast majority of the universe's mass but remain elusive to direct detection. If kekos turn out to be related to these exotic forms of matter, they could open a direct observational window into the elusive substances that dominate the cosmos. Beyond their potential connection to dark matter, kekos could also provide a valuable new tool for studying the most extreme environments in space. The study of black holes has already provided groundbreaking insights into the nature of gravity, time, and space. By extending our research to include kekos, we could unlock entirely new insights into the behavior of matter under extreme conditions, challenging our current understanding of how forces like gravity and electromagnetism interact in the presence of extremely dense objects. Another intriguing possibility is that kekos could play a role in understanding the behavior of spacetime itself. In Einstein's general theory of relativity, spacetime is described as a fabric that is warped by the presence of mass and energy. The more massive an object is, the greater its curvature of spacetime. Black holes, for example, represent regions where spacetime is curved to such an extent that not even light can escape. However, the extreme conditions around kekos could present an entirely different kind of spacetime curvature. If kekos are truly stable, despite their extreme densities, this could indicate a new way that matter interacts with the fabric of spacetime. If these objects exist, they could provide us with direct evidence of how gravity behaves in the quantum regime, something that has remained elusive to scientists for decades. The concept of quantum gravity seeks to unify general relativity, which governs the large-scale structure of the universe, with quantum mechanics, which describes the behavior of subatomic particles. These two theories have been incredibly successful in their own domains, but when it comes to extreme conditions, like those near black holes or within the core of neutron stars, they break down. The study of kekos could offer a unique opportunity to probe these extreme environments, potentially revealing how quantum mechanics and gravity work together at the most fundamental level. As we continue to refine our observational techniques, the search for kekos could yield unexpected discoveries. The advanced tools available to astronomers today, such as the Event Horizon Telescope and gravitational wave observatories, have already enabled us to observe phenomena that were once thought to be beyond our reach. These technologies allow us to peer into the hearts of distant galaxies and study the behavior of massive objects in ways that were previously impossible. If kekos exist, it's likely that these observatories will be instrumental in uncovering their presence. Whether it's through direct observation of their gravitational effects or indirect evidence from the way they influence nearby objects, the detection of kekos would be one of the most exciting discoveries in modern astrophysics. In addition to their potential implications for fundamental physics, kekos could also impact our understanding of the universe's evolution. The formation and distribution of compact objects like black holes and neutron stars play an essential role in the dynamics of galaxies. If kekos are part of this mix, they could influence the formation and behavior of galaxies and other cosmic structures. Their unique properties might affect the way galaxies interact with one another, or even help to explain some of the observed large-scale structures in the universe, such as galaxy clusters or cosmic voids. There is also the possibility that kekos could provide insights into the fate of the universe itself. Some theories suggest that the evolution of compact objects could be tied to the ultimate fate of the cosmos. Will the universe continue expanding forever, or will it eventually collapse in on itself in a big crunch? The study of kekos could help shed light on this question by offering clues about how objects behave under the influence of extreme gravity, and how the universe's largest structures interact over time. Their stability, or lack thereof, could provide important information about the long-term behavior of the cosmos. The search for kekos represents a fascinating journey into the unknown, one that holds the promise of expanding our understanding of the universe in ways we can scarcely imagine. Whether they are composed of exotic forms of matter, related to dark matter, or governed by yet undiscovered physical laws, the existence of kekos would mark a groundbreaking chapter in the story of cosmology. And as we continue to explore the farthest reaches of space, we may one day uncover the secrets of these strange, mysterious objects, unlocking new truths about the very nature of reality itself. As we push the boundaries of what we know, the potential discovery of quasi-stable exotic compact objects, kekos, could fundamentally alter our understanding of both the small-scale and large-scale structure of the universe. These objects are more than just a theoretical curiosity. They may be the key to answering some of the most pressing questions in modern physics. Their existence could be a critical piece of the cosmic puzzle that ties together the mysteries of gravity, matter, energy, and the fundamental forces that govern everything from the smallest subatomic particles to the grandest galaxies. When we consider the extreme conditions in which kekos might form, it becomes clear that these objects occupy a unique place in our understanding of astrophysical phenomena. While much of the universe is governed by familiar forces like electromagnetism and gravity, kekos could represent an entirely new class of objects, governed by yet unseen forces or interactions that we have yet to fully understand. It's possible that these objects might exhibit behaviors that differ from anything we have observed before, such as the potential to maintain a quasi-stable state without collapsing into a singularity or becoming a black hole. This new class of compact objects challenges the way we think about the end stages of stellar evolution. While conventional theories have long predicted that massive stars either collapse into neutron stars or black holes after exhausting their fuel, kekos present an alternative possibility, one in which matter and energy do not follow the expected path. The potential for quasi-stable equilibrium in such objects could open up entirely new avenues of research, especially when considering how these objects would interact with the surrounding environment. Imagine a keko existing in a distant galaxy, nestled within the dense core of a star cluster. Its existence would be marked by its extreme density and gravitational effects, yet it would not succumb to the fate of a black hole. Instead, it would maintain a delicate balance between the immense inward pull of gravity and the outward forces acting upon it. This would make kekos valuable laboratories for studying the interplay of these forces in real time. The observations made of such objects could provide us with insights into the processes that drive the formation of galaxies, stars, and even black holes, offering a deeper understanding of cosmic evolution. As these objects could potentially exist in states of high energy, they could also serve as natural laboratories for studying the fundamental forces of nature under extreme conditions. Gravitational forces would be incredibly strong near a keko, leading to the potential for exciting observations about the behavior of light, time, and space near such objects. The potential for gravitational wave emissions, similar to those produced by the collision of black holes, could provide another avenue for detection, allowing us to observe these enigmatic objects from vast distances. Moreover, kekos could be closely tied to the fabric of spacetime itself. In general relativity, spacetime is described as a smooth, curved entity that is influenced by mass and energy. But near a keko, the curvature of spacetime could exhibit unusual properties, potentially revealing new aspects of the nature of gravity at both the macroscopic and microscopic scales. This could have profound implications for our understanding of quantum gravity, a field that seeks to unify the principles of quantum mechanics with those of general relativity. In this context, kekos could provide a unique testing ground for theories of quantum gravity, offering us a glimpse into a realm where the known laws of physics may not apply in the same way. Another important feature of kekos is the potential for the formation of singularities, or the lack thereof. While black holes are known for their singularities, regions where gravity becomes infinite, kekos may avoid the formation of these singularities altogether. Instead of collapsing into an infinitely dense point, these objects might maintain a stable state that resists gravitational collapse. This presents a fascinating contrast to the classical model of black holes, which suggests that no such stability is possible beyond a certain point of compression. The absence of a singularity could have wide-ranging implications for our understanding of the nature of spacetime, and might even offer clues about the possibility of life beyond the event horizon of black holes. Theoretical physicists have already begun to model how kekos might form, and how they could evolve over time. Some models suggest that they could arise from the collapse of certain types of massive stars, especially those that are not massive enough to form a black hole but too massive to form a stable white dwarf or neutron star. Instead of collapsing all the way down to a singularity, these stars might stabilize at a certain density, creating a quasi-stable compact object that resists further collapse. Alternatively, kekos might form as the result of exotic matter, such as quark matter or strange matter, that behaves differently from the matter we are familiar with. Theoretical work on the properties of strange quark matter, in particular, suggests that such matter could form stable, compact objects that do not exhibit the same properties as regular matter. For all their theoretical appeal, the detection of kekos remains a significant challenge. Traditional methods of observing astrophysical objects, such as optical telescopes, radio telescopes, and X-ray observatories, are designed to detect the kinds of radiation emitted by more conventional objects like stars and black holes. Kekos, however, might not emit detectable radiation in the same way, or at all. Instead, their existence might be inferred from their gravitational effects on nearby objects, or from the bending of light around them. This gravitational lensing effect could allow us to detect their presence, but only if we are able to observe the right conditions and identify the subtle distortions in spacetime that would indicate their existence. One promising technique for detecting kekos could involve the use of gravitational wave observatories, such as the Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo. These observatories are designed to detect ripples in spacetime caused by the acceleration of massive objects, such as merging black holes or neutron stars. Kekos, if they exist, could produce gravitational waves when interacting with other massive objects, such as stars or black holes. These waves could be detected by existing gravitational wave observatories, providing us with a new means of detecting and studying kekos from a distance. Another method that might be used to detect kekos involves studying the effects of their presence on the surrounding cosmic environment. For example, kekos could influence the motion of nearby stars or gas clouds, causing them to move in unusual ways. These effects could be detected by observing the motions of objects in the vicinity of a suspected keko, and could provide indirect evidence of its existence. Similarly, the effect of kekos on the cosmic microwave background radiation, the afterglow of the Big Bang, could provide important clues about their presence, as these objects might leave subtle imprints on the radiation that travels through space. Despite these challenges, the potential rewards of discovering kekos are immense. If these objects turn out to exist, they could provide a wealth of information about the fundamental nature of matter, gravity, and the universe itself. Kekos could provide insights into the behavior of exotic matter under extreme conditions, the nature of spacetime, and the origins of some of the most enigmatic phenomena in the cosmos. Their study could lead to breakthroughs in our understanding of quantum mechanics, general relativity, and the fundamental forces that shape the universe. As we continue to develop new observational techniques and improve our theoretical models, the possibility of detecting kekos becomes more and more plausible. Whether they are related to dark matter, formed from exotic matter, or governed by new forces that we have yet to fully understand, kekos could represent one of the most significant discoveries in modern astrophysics. By studying these objects, we may be able to unlock some of the deepest mysteries of the universe, shedding light on the nature of gravity, spacetime, and the fundamental forces that govern everything from the smallest particles to the largest cosmic structures. The search for kekos represents the cutting edge of astrophysical research, a journey into the unknown that could reveal new truths about the very nature of reality. Whether they are destined to be found or remain theoretical objects, the pursuit of knowledge about these exotic entities will continue to inspire future generations of scientists, challenging them to push the limits of our understanding of the cosmos. As we continue to probe the depths of space and uncover the mysteries that lie beyond our current comprehension, the quest for kekos will remain one of the most exciting and promising avenues of exploration in the field of astrophysics. As we continue to venture further into the realms of theoretical astrophysics, the possibility of discovering quasi-stable exotic compact objects, kekos, challenges not only the current understanding of stellar evolution but also our entire framework of how matter and energy interact under extreme conditions. The search for these objects could uncover entirely new dimensions to the physical world that remain hidden in the shadow of known physics. Their potential to unlock secrets of the universe extends far beyond merely adding another object to the catalog of astrophysical phenomena. They may represent a key to resolving some of the most fundamental questions about the universe's structure, origin, and ultimate fate. A critical aspect of kekos that has generated considerable interest is their possible connection to dark matter. Dark matter, which constitutes a significant portion of the universe's mass but remains invisible to all forms of detection except through its gravitational influence, has been one of the most elusive and perplexing components of modern cosmology. Despite decades of effort, the exact nature of dark matter remains unknown, with various hypotheses ranging from weakly interacting massive particles, WIMPs, to axions, sterile neutrinos, and more. Kekos might provide a crucial piece of the dark matter puzzle, offering a potential explanation for the unseen gravitational effects we observe across galaxies and clusters. If kekos were discovered to be composed of exotic, dark matter-like material, perhaps involving forms of quark matter, strange matter, or other unknown states of matter, this could directly link these objects to the ongoing mystery of dark matter. In this case, kekos could represent some of the first tangible evidence of dark matter, which has thus far been inferred only through indirect observations. Understanding the behavior of these objects would give us insight into how dark matter interacts with normal matter, revealing new aspects of cosmic interactions that have remained hidden for centuries. By observing the gravitational effects of kekos, astronomers might begin to distinguish the specific properties of dark matter that would otherwise elude detection. In addition to dark matter, kekos could provide a window into the realm of quantum gravity. The unification of general relativity, which governs the macroscopic world of planets, stars, and galaxies, with quantum mechanics, which governs the microscopic world of particles and forces, is one of the greatest challenges in physics. To date, these two theories have remained largely incompatible, and scientists have been searching for a theory of quantum gravity that could bridge the gap between the two. Kekos might offer the key to unlocking this mystery, as their extreme density and unusual properties could create conditions where the effects of both general relativity and quantum mechanics are significant and observable. One theory proposes that the extreme gravitational fields of kekos might lead to the formation of quantum fluctuations in spacetime itself, possibly giving rise to exotic phenomena such as spacetime foam. In this framework, the very fabric of spacetime at microscopic scales might become unstable and fluctuate, creating unpredictable distortions in the way that time and space behave. These fluctuations could offer crucial evidence for the existence of quantum gravity, giving scientists a rare opportunity to directly observe its effects and begin testing theories that could eventually lead to a unified understanding of the fundamental forces of nature. The potential discovery of kekos could also have profound implications for our understanding of the ultimate fate of the universe. The presence of these quasi-stable objects could provide critical insights into the final stages of cosmic evolution. While black holes are traditionally thought to represent the end point for massive objects, kekos might offer a more complex and nuanced picture. These objects, while incredibly dense, might not collapse into singularities, and they could maintain a stable, albeit exotic, existence for much longer than conventional models would predict. Such stability could provide a unique look at the long-term evolution of the universe, potentially offering a glimpse of what the cosmos might look like in the far future. As stars burn out and galaxies drift apart, kekos might survive, standing as one of the last remnants of a more dynamic and energetic universe. Their continued existence might give rise to new forms of astrophysical phenomena that we have yet to imagine, reshaping our understanding of the universe's fate in ways that we cannot fully predict. In a sense, kekos could be a cosmic bridge, offering clues about both the past and the future of the universe. The broader implications of kekos stretch into the realms of science fiction and beyond. If these objects turn out to be as stable and long-lived as some models suggest, they could provide a unique environment for the development of new kinds of astrophysical processes and even forms of life, though the latter remains speculative at best. What we do know is that their study could open entirely new fields of research, expanding the horizons of physics, cosmology, and astronomy. As researchers continue to study kekos and their potential properties, new observational techniques and instruments will be necessary to detect them. For instance, we may need to develop more advanced space-based telescopes that can capture faint and subtle signals that might otherwise go unnoticed. The technology to study kekos may include improvements in gravitational wave detectors, which could provide a more direct method of observing their interactions with other massive objects. Advances in particle physics could also lead to the development of new detectors that can measure exotic forms of matter, potentially giving us the ability to observe these objects in a more direct manner. Furthermore, the possibility of detecting kekos using gravitational wave astronomy cannot be overstated. As gravitational wave detectors become more sensitive, they could reveal new and unexpected sources of these waves. The detection of gravitational waves from the mergers of kekos, or even from the interactions between kekos and other exotic objects, could provide a groundbreaking discovery that reshapes our understanding of astrophysics and cosmology. This would mark a new era in the study of the universe, where observations no longer rely solely on electromagnetic radiation, but instead utilize the very fabric of space-time itself to gain insights into the universe's most elusive phenomena. The study of kekos may also reveal more about the fundamental structure of matter. As these objects challenge our current models of compact objects, they could force physicists to reconsider the nature of matter under extreme pressure and temperature. The theoretical frameworks that govern the behavior of matter at such high densities might be rewritten, offering new insights into the quantum properties of particles and fields. The research into these objects could result in the development of new theories in both theoretical and experimental physics, as scientists attempt to model and simulate the behavior of these exotic, dense objects. Furthermore, the continued exploration of kekos might encourage new ideas about the origins of the universe and the fundamental forces that drive its expansion. These objects, while incredibly rare, may represent a key to understanding how the universe came into being and what forces shaped its early evolution. Understanding the role of kekos in the broader context of cosmic formation could lead to more precise models of galaxy formation, star birth, and the development of the fundamental building blocks of the universe. The potential discovery and study of quasi-stable exotic compact objects hold the promise of revolutionizing many fields of astrophysics, from our understanding of gravity and quantum mechanics to the behavior of matter under extreme conditions. Kekos could provide us with a new lens through which to explore the most enigmatic aspects of the universe, and their study could help us answer questions that have puzzled scientists for centuries. Whether they are composed of exotic matter, linked to dark matter, or governed by unknown physical forces, these objects could reveal new insights into the nature of reality itself. The quest to uncover the secrets of kekos is only beginning, but its potential to reshape our understanding of the universe is boundless. As we continue our exploration into the realm of quasi-stable exotic compact objects, kekos, it becomes clear that these objects are not merely theoretical curiosities. They represent a profound and potentially transformative avenue for understanding the universe at its most fundamental level. While we are still in the early stages of their study, the implications of their discovery or creation could ripple through multiple fields of science, from the smallest particles of matter to the vast expanses of the cosmos. One intriguing aspect of kekos is their potential to challenge and expand our understanding of stellar remnants. Traditionally, when a massive star exhausts its nuclear fuel, it undergoes one of two well-understood processes. If the star is not massive enough, it will shed its outer layers and become a white dwarf. If it is sufficiently massive, the star will collapse under its own gravity, forming a black hole. But what happens when a star's mass and composition fall in between these extremes? Could kekos exist as an intermediate state of stellar evolution, a stage that is neither a white dwarf nor a black hole, but rather something more complex and exotic? This question is particularly intriguing when we consider the potential for a third way in stellar remnants, something that does not fully collapse into a singularity or remain in a stable, non-collapsed state. Kekos may represent this third path. They would sit at the border between a fully collapsed object like a black hole and a stable, yet highly dense, object like a white dwarf. Their stability, under extreme gravitational and quantum mechanical conditions, could challenge our definitions of stellar remnants entirely. But it's not just their formation that poses an intellectual challenge, it's their very nature. The study of kekos might offer insights into the very fabric of spacetime itself. Their quasi-stable status suggests that they could exist for extended periods without collapsing into more familiar objects, like black holes. This presents the possibility that there could be an unknown form of matter or energy at play, one that doesn't adhere to conventional laws of physics. Understanding kekos might involve delving deep into the study of exotic matter, states of matter that are different from those we typically encounter. For instance, strange quark matter could be involved, or perhaps some form of condensed matter physics operating at an extreme scale. The density of these objects could be so high that traditional models of matter and energy begin to break down. At such high densities, atomic structure might not exist in the way we understand it. Instead, the matter might exist in a form we cannot yet describe fully, and it could have profound implications for both the structure of matter and the nature of space itself. Further complicating this picture is the possibility that kekos might not just be theoretical objects confined to distant regions of space. If they exist, there could be implications for phenomena closer to home. For example, our galaxy could contain such objects, quietly influencing the orbits of nearby stars or even acting as gravitational lenses, magnifying and distorting the light from more distant stars. These quiet but powerful objects might go unnoticed by current observational techniques, but their existence could explain anomalies in star movements and gravitational behaviors that seem to defy explanation. The study of kekos also invites questions about the very limits of the known universe. As we push the boundaries of science and technology, we may discover that the universe is far stranger and more complex than we had ever imagined. The detection of kekos could reveal a range of new phenomena that we have not yet encountered, potentially giving us a glimpse into the hidden aspects of the universe that are typically obscured by our limited observational capabilities. These objects could push the boundaries of physics to the breaking point, revealing new laws of nature that we have yet to uncover. As the scientific community continues to develop better tools for observing the universe, it's likely that the discovery of kekos will be one of the most profound breakthroughs in the coming decades. Observational technologies such as gravitational wave detectors and space-based telescopes are improving every year, and these advancements may soon enable us to detect the faint signals produced by these mysterious objects. Their gravitational interactions, the way they distort spacetime, and the way they interact with light will provide astronomers with the clues they need to confirm their existence. In the future, we may also develop new theoretical models that better explain how kekos form and what their long-term stability implies. Perhaps they are relics of the early universe, objects that formed during the most chaotic moments following the Big Bang. Maybe they are the remnants of collapsed stars that never quite reached the threshold for becoming black holes. Alternatively, they could be manifestations of entirely new physics, requiring us to rethink our understanding of gravitational collapse, quantum mechanics, and the interaction of exotic matter. What is certain is that kekos will challenge our ideas about the boundaries between what we consider to be normal matter and what exists in the realm of the unknown. Their discovery could serve as the key to unlocking the deeper mysteries of the cosmos, such as the nature of dark matter, the structure of the early universe, and the ultimate fate of collapsed stars. And in doing so, they could change everything we thought we knew about the universe. In the grand scheme of cosmic evolution, these objects might represent a new class of phenomenon that fits into a larger cosmic narrative. We currently view the life cycle of stars as a well-understood sequence: birth, evolution, death, and either collapse or stable end. But kekos, with their potential to remain quasi-stable for long periods, might suggest a more complex and nuanced view of stellar evolution. They could be the universe's quiet survivors, persisting long after other forms of matter have decayed or collapsed. Furthermore, the existence of kekos could prompt a reevaluation of the final fate of the universe itself. If kekos remain stable for billions or even trillions of years, they might outlast other forms of matter, standing as the last vestiges of an ancient universe. In such a scenario, kekos could become the universe's final remnants, quietly evolving and interacting under the influence of forces and laws of physics we are just beginning to understand. In this way, they might offer a glimpse into the distant future of the universe, when all other forms of matter have dispersed or collapsed. And perhaps most intriguingly, the study of kekos could help bridge the gap between the quantum and cosmic scales. In the ongoing search for a theory of quantum gravity, these objects might offer a testing ground for some of the most difficult and mysterious questions in physics. The relationship between gravity and quantum mechanics has long been a topic of debate and investigation, but a clear, unified theory remains elusive. Kekos could potentially be the physical manifestation of these forces acting together, providing us with a window into how they interact on scales far beyond the reach of current experiments. As research into kekos continues to unfold, one thing is clear: the discovery of these exotic objects will undoubtedly reshape our understanding of the universe. Whether they are composed of dark matter, strange matter, or other exotic substances, they will push the boundaries of what we know about the cosmos, presenting us with new mysteries and challenges. Their study could revolutionize not just astrophysics, but also our entire view of the physical world, leading us toward an understanding of the universe that goes far beyond what we thought possible. In the coming years, the hunt for kekos will likely intensify, and new discoveries will continue to emerge. As scientists develop new tools and techniques to observe and study these mysterious objects, they may unlock secrets that change the course of human understanding of the universe forever. Whether or not kekos exist, and what their discovery might ultimately mean, remains an open question, but the search for answers is bound to redefine the future of science itself. As we look ahead to future research into quasi-stable exotic compact objects, kekos, there are several key questions that remain unanswered, driving the scientific community forward. How do we detect these objects in the vast and ever-expanding universe? What kind of theoretical frameworks can explain their formation and their behavior over time? And perhaps most profoundly, what do kekos reveal about the fundamental nature of space, time, and the laws that govern them? One of the main obstacles to studying kekos is the difficulty in detecting them. Unlike more familiar objects such as stars, planets, or black holes, kekos do not emit significant amounts of light or radiation that can be picked up by traditional telescopes. They may not even produce detectable gravitational waves, at least not in the same way that merging black holes or neutron stars do. This makes their observation extraordinarily difficult, especially given that they might be small and cold, existing in the dark corners of space where the conditions are ideal for their formation but where observational techniques are limited. However, the future of astronomy is being shaped by advanced technologies designed to probe deeper into the universe. The next generation of gravitational wave detectors, like the planned upgrades to LIGO, Laser Interferometer Gravitational Wave Observatory, may allow us to detect more subtle signals from objects like kekos. These detectors could pick up on the tiny distortions in spacetime caused by the gravitational interactions of these exotic objects. Such signals would be faint and difficult to distinguish from the noise of other cosmic phenomena, but with enough precision and sensitivity, kekos might be detected in the future. In addition to gravitational waves, electromagnetic radiation may also play a role in the detection of kekos. While they may not emit visible light, it's possible that these objects could produce faint radiation in other parts of the spectrum, such as in the infrared or radio wavelengths. As we develop more advanced telescopes, such as the James Webb Space Telescope, JWST, we may be able to capture more subtle emissions that provide clues to the presence of kekos. By studying the interaction of light with the objects in the surrounding space, astronomers may be able to infer the presence of these exotic objects, even without direct observation. Another possible avenue for the detection of kekos involves the study of gravitational lensing. gravitational lensing occurs when a massive object distorts the path of light passing through it, creating a magnifying effect. This phenomenon is most commonly observed with large objects like galaxy clusters or black holes, but it is conceivable that kekos, with their dense and gravitationally intense nature, could also act as gravitational lenses. If a keko passes between us and a distant source of light, such as a star or another galaxy, it might distort the light in a way that could provide indirect evidence of its existence. This method, while indirect, could offer astronomers a new way to search for kekos in the vastness of space. As our observational tools continue to evolve, so too will our understanding of these enigmatic objects. The advent of more powerful computers and more sophisticated simulations will allow us to model kekos with greater accuracy. By simulating their formation, behavior, and potential interactions with other celestial bodies, scientists will be able to test theories and predict what kind of observable effects they might have. These simulations will provide valuable insights into how kekos could be integrated into our broader understanding of the universe, bridging the gap between theoretical predictions and empirical observations. The key to unraveling the mysteries of kekos lies in the careful synthesis of theory and observation. We can already begin to imagine the ways in which kekos might impact our understanding of fundamental physics. Their existence could challenge current models of stellar collapse, black holes, and quantum mechanics. For example, the fact that kekos may exist in a quasi-stable state, either fully collapsed into a black hole nor fully stable like a white dwarf, suggests that our current models of matter under extreme conditions may need to be revised. These objects could hold the key to understanding the strange behavior of matter at the threshold of black hole formation, and might even reveal new physics beyond the standard model. Moreover, the study of kekos could provide insights into the enigmatic nature of dark matter. While dark matter remains invisible to us through conventional means of observation, its gravitational effects are undeniable. Kekos, with their extreme densities and gravitational interactions, could potentially be linked to dark matter in some way. They may even provide a window into the properties of dark matter, suggesting that it could take forms other than the mysterious WIMPs, weakly interacting massive particles, that are currently the focus of dark matter research. This connection, if confirmed, could have profound implications for our understanding of the universe's composition. Beyond their potential to expand our understanding of matter and energy, kekos could also help us explore more speculative, yet tantalizing ideas about the fabric of spacetime itself. Some theories in physics suggest that spacetime is not a smooth, continuous entity, but rather, it could be made up of discrete, quantum-scale, atoms, or loops, of spacetime. If kekos exist and exhibit unique quantum mechanical behaviors under extreme conditions, they could provide experimental evidence for these more radical theories. Their study might help physicists probe the limits of spacetime and the behavior of gravity at the quantum level, which has long eluded direct experimental confirmation. Furthermore, kekos may offer a unique opportunity to test theories of quantum gravity. Currently, one of the most pressing challenges in theoretical physics is the lack of a unified theory that combines quantum mechanics with general relativity, Einstein's theory of gravity. The intersection of these two domains is a frontier of modern physics, and kekos could play a central role in testing ideas like string theory, loop quantum gravity, and other approaches to quantum gravity. By studying the properties of kekos and their interactions with light, matter, and gravity, scientists may uncover the first tangible clues about how these two seemingly incompatible theories can be reconciled. In essence, the pursuit of kekos represents much more than a search for exotic astronomical objects. It is a quest to understand the deepest, most fundamental aspects of the universe, to probe the nature of matter, energy, and the very structure of spacetime itself. The questions surrounding kekos are not just theoretical, they touch upon the very nature of reality. If these objects exist, they could provide us with a new, unprecedented lens through which to view the cosmos, a lens that might reveal new physical principles, new forces, and new realms of scientific exploration. Ultimately, the discovery of kekos, while still a long way off, could be one of the most exciting and transformative breakthroughs in modern physics. They represent the cutting edge of our understanding of the universe and offer the tantalizing prospect of unlocking some of the most profound mysteries of existence. Whether they are the remnants of stars that never fully collapsed, or entirely new forms of matter that challenge our fundamental concepts, kekos could become one of the defining objects of future research. As we continue to push the boundaries of science and technology, it is possible that kekos will be the key to unlocking some of the deepest questions of all. What is the true nature of the universe, and how does it work at its most fundamental level? In the coming years, we will continue to refine our models, develop new observational tools, and test new theories that may finally reveal the existence of these enigmatic objects. As we do, we move ever closer to understanding the nature of reality itself, one that may be far stranger and more complex than we ever imagined. The search for kekos is a search for the unknown, and it is this very uncertainty that makes the pursuit so thrilling. Because in science, as in life, the most exciting discoveries often lie just beyond the horizon, waiting to be uncovered. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.